Hello there and welcome to Life Beyond Seen, where curiosity settles in quietly, the pace stays unhurried, and science becomes something you can listen to without needing to brace yourself for urgency. This is a place for slow explanations, gentle fascination, and the kind of topics that invite interest without demanding effort. Tonight's subject drifts far below everyday experience, down past coastlines, below familiar fish and coral reefs, into regions of the ocean most people will never see in person. We're talking about the deepest parts of the ocean, and more specifically why those depths often look so unfamiliar, sometimes unsettling, occasionally even described as alien. That word, alien, gets used a lot when people see footage from deep-sea expeditions. It pops up in documentaries, headlines and casual conversations. Someone sees a fish with a transparent head, a squid with glowing spots, or a creature with a mouth that seems too large for its body, and the immediate reaction is often, "That doesn't look like it belongs on Earth." The interesting thing is that these organisms absolutely do belong here. They evolved here, they fit their environment precisely, and from a biological perspective they make perfect sense. It is our expectations, shaped by surface life, that make them appear strange. Before going further, take a moment to notice where you're listening from tonight. Maybe you are at home winding down after a long day, maybe travelling, maybe somewhere quiet, maybe somewhere with a bit of background noise. And what time is it where you are right now? There is something slightly amusing about discussing the darkest parts of the ocean while people across different time zones listen, under very different lighting conditions, some in daylight, some already in darkness, all connected by the same stream of sound. If you find this kind of calm exploration enjoyable, if it works well as background listening, relaxation, or simply a way to learn something without pressure, consider giving the video a like and possibly subscribing. It helps this slow-paced corner of science reach others who might appreciate a quieter approach. No rush on that, of course. Just something to keep in mind while we continue. So, about those deep ocean environments. Most of the planet's living space is actually down there. Oceans cover roughly 70% of Earth's surface, and the majority of that water is deep, very deep. We often picture Earth in terms of continents, cities, mountains and skies, but from a strictly spatial perspective, the dominant environment is cold, dark seawater extending kilometres downward. Humans, being land mammals with lungs and limited pressure tolerance, mostly experience only the upper skin of that vast system. The deeper you go, the more conditions change. Sunlight fades quickly, temperature drops, pressure increases at a rate that would crush unprotected human bodies long before reaching the deepest trenches. Food becomes scarce, currents behave differently, and visual communication starts losing usefulness because there simply is not enough light. These factors combine to shape organisms in ways that can look unfamiliar when compared with animals that evolved in well-lit, moderate environments. It helps to remember that alien-looking is usually just shorthand for adapted to conditions we rarely encounter. If humans lived permanently several kilometres underwater, surface animals might look equally odd to us. Bright colours, delicate bones, reliance on sight, and air breathing would seem impractical from that perspective. Another piece of the puzzle is expectation. Many people subconsciously assume life should resemble the animals they grew up seeing. Fish should have certain proportions, eyes should look a certain way, movement should follow patterns we recognise. When those expectations get disrupted, the reaction is often surprise rather than understanding. A deep-sea anglerfish with a bioluminescent lure makes perfect evolutionary sense, but it contradicts the mental template of what a fish should look like. There is also the simple matter of exposure. Surface wildlife appears in daily life, media, art, and education. Deep-sea organisms rarely do. Limited familiarity makes anything appear unusual. A creature that is commonplace to marine biologists may still seem extraordinary to someone seeing it for the first time, and then there is lighting, or rather the lack of it. Most deep-sea footage comes from submersibles equipped with strong artificial lights. Those lights illuminate animals in stark contrast against black water, which can exaggerate features, flatten depth perception, and remove environmental context. Imagine seeing a deer only through a spotlight at night with no surrounding landscape visible. Even familiar animals can look odd under those conditions. Pressure plays a role as well. At depths of several thousand meters, pressure can exceed several hundred times what we experience at sea level. Gas-filled cavities become problematic. Flexible tissues, reduced skeletal density, and unusual body compositions become advantageous. Some fish look gelatinous because rigid structures are less useful under extreme pressure. When brought to the surface, they sometimes deform, reinforcing the perception that they are unnatural, when in fact they simply lost the pressure they rely on. Temperature influences things too. Deep waters are typically cold, often just above freezing. Metabolic rates slow. Movement becomes economical. Growth patterns differ. Animals may live longer, mature later, and conserve energy in ways that contrast with more active shallow water species. These adaptations can affect body shape, behaviour, and even facial structure. Food scarcity shapes anatomy noticeably. In an environment where meals are unpredictable, large mouths, expandable stomachs, and opportunistic feeding strategies become useful. Some fish can swallow prey nearly their own size because passing up a rare food opportunity could mean a very long wait for the next one. From a surface perspective, oversized jaws can look intimidating or exaggerated, but functionally they are practical. Sound replaces vision in some contexts. Vibrations travel efficiently through water, so sensory systems tuned to pressure waves, electrical fields, or chemical cues can be more reliable than eyesight. Reduced eyes or highly specialized sensory organs are logical outcomes, though again they may seem unusual when compared with animals that rely heavily on vision. Bioluminescence deserves a brief mention here because it is one of the features people often associate with alien appearances. Many deep-sea organisms produce light chemically. This can serve multiple purposes: attracting prey, communication, camouflage through counter-illumination, or startling predators. Because humans associate self-generated light mostly with technology rather than biology, glowing animals can feel unexpected. There is also scale variation. Some deep-sea species exhibit gigantism compared with their shallow relatives, while others remain extremely small. Environmental stability, low predation in some zones, and energy efficiency considerations all contribute. Without familiar reference points, size perception can become skewed in photographs and videos, adding to the impression of strangeness. Technology has expanded our view significantly over the past century. Early ocean exploration barely scratched the surface. Modern remotely operated vehicles, advanced sonar mapping, deep diving submersibles, and high-sensitivity cameras now provide clearer glimpses of life at depth. Every improvement reveals organisms that were previously unknown, which periodically renews public fascination. Even so, large portions of the deep ocean remain underexplored. Some estimates suggest we have mapped less of the seafloor in high detail than certain planetary surfaces. That ongoing discovery process contributes to the perception of mystery. Unknown environments invite speculation, and speculation often leans toward the dramatic. Cultural factors add another layer. Literature, films, and folklore frequently portray the deep sea as a place of monsters or hidden worlds. Those narratives shape expectations long before people see actual scientific footage. When real animals appear unusual, they can easily get folded into those pre-existing story frameworks. There is also a psychological element tied to darkness itself. Humans evolved primarily as daytime creatures with limited night vision. Darkness historically implied uncertainty or potential danger. Deep ocean darkness amplifies that instinctive caution. Combine darkness with unfamiliar shapes, and the mind fills gaps quickly. Despite all that, marine biologists tend to view these animals not as alien, but as elegant solutions to environmental challenges. efficiency, conservation of energy, sensory optimization, and reproductive strategies all align closely with local conditions. Once those conditions are understood, appearances start making sense. Another interesting point involves reproduction. Sparse populations in vast environments require strategies that maximize encounter chances. Some species release gametes widely, some use chemical signals to coordinate spawning, and a few have developed extremely specialized mating systems. These reproductive adaptations sometimes influence morphology in ways that look unusual. Movement patterns differ too. Rapid swimming wastes energy where food is scarce. Drifting, hovering, or slow cruising becomes common. Body shapes that minimize energy expenditure rather than maximize speed are advantageous. From a surface perspective, slower motion can seem eerie, but it is simply efficient. Coloration shifts with depth. Bright reds appear black under blue-filtered deep water light. Transparency becomes a form of camouflage. Reflective surfaces can scatter faint light. Again, these are practical adaptations, though they can create striking visual impressions under artificial lighting. Scientific curiosity about these ecosystems continues growing because they influence global processes more than many realize. Carbon cycling, nutrient transport, climate interactions, and biodiversity reservoirs all connect to deep-sea dynamics. Understanding them is not just academic, it has practical implications. There is also increasing awareness of human impact. Deep-sea mining proposals, fishing expansion, pollution, and climate-driven changes in ocean chemistry may affect habitats that took millennia to stabilize. Studying these areas helps inform decisions before irreversible changes occur. Public interest often spikes when dramatic footage emerges, like newly discovered species or unusual behaviors captured on camera. Those moments remind people that exploration on Earth is far from complete. Space exploration gets attention, but ocean exploration remains equally compelling in its own way. As we continue easing into this topic, the next step naturally involves looking more closely at what happens just below the surface, where sunlight begins to fade and familiar marine life starts giving way to organisms adapted to dimmer conditions. That gradual transition helps explain why the deepest zones end up looking so different, and it sets the stage for understanding how light, pressure, temperature and time shape life step by step rather than all at once. When people imagine the ocean, the first picture that usually comes to mind is the surface. Sunlight reflecting off waves, maybe a beach somewhere, maybe boats, swimmers, seabirds, or a calm horizon. It looks familiar, comfortable, easy to understand, but that surface layer is extremely thin compared with what lies below it. The moment you move beneath it, even just a few meters, the environment begins changing in ways that are subtle at first, then increasingly noticeable. That early descent is where the first hints of unfamiliarity start appearing, long before the extreme depths. Just below the surface, sunlight is still strong. Colours look normal, movement is active, and the animals that live there resemble what most people think of when they hear the word fish. Reef fish. Schools of sardines, tuna, sharks, sea turtles. Their shapes are streamlined for swimming. Their eyes are adapted for daylight, and many rely heavily on vision to navigate, hunt, or avoid predators. At this stage, nothing seems particularly alien. It feels like an extension of the world above water, simply with different rules for breathing and movement. But sunlight does not penetrate water the same way it travels through air. Water absorbs light quickly, and different wavelengths disappear at different depths. Reds fade first, often within just a few meters. Oranges follow, yellows gradually weaken, blues travel the farthest, which is why the open ocean often appears blue from above. That colour filtering changes how animals look. A red fish deeper down can appear nearly black because the red wavelengths needed to reflect its colour are no longer present. This shift alone can make familiar animals seem oddly coloured or shadow-like. Temperature begins shifting as well. Surface waters are warmed by sunlight, but deeper layers receive less energy. In many regions, there is a thermocline, a layer where temperature drops more rapidly with depth. Passing through it can feel noticeable even to divers wearing protective gear. Marine animals crossing this boundary experience changes that affect metabolism, activity levels, and sometimes migration patterns. Some species move vertically daily, feeding near the surface at night and retreating deeper during the day to avoid predators. Pressure increases steadily. Every 10 meters or so of depth adds roughly 1 atmosphere of pressure. Humans rarely notice this without equipment, but marine organisms are constantly adapted to it. Swim bladders, gas exchange systems, skeletal structures, and tissue composition all reflect pressure conditions. Fish that live near the surface often cannot survive rapid descent, and deep-dwelling species struggle if brought upward too quickly. The early depth changes are manageable, but they signal the trend that will continue all the way down. Visibility changes too. Even before true darkness, the quality of light shifts. Shadows soften, contrast reduces, details blur slightly. Suspended particles scatter light, creating a hazy appearance compared with air. That visual softness encourages reliance on other senses. Lateral line systems in fish detect vibration. Chemical cues travel through water efficiently. Electrical sensing exists in some species. These systems begin gaining importance as depth increases. Movement patterns start adjusting as well. Surface waters are dynamic. Waves, tides, wind-driven currents and temperature mixing create constant motion. Slightly deeper water can be more stable. Some animals prefer that stability. Jellyfish, comb jellies and drifting plankton communities often inhabit mid-water zones where currents transport them slowly. Their bodies reflect this lifestyle. Delicate, gelatinous, sometimes transparent, they conserve energy by letting water movement do much of the work. Transparency is worth noting because it often surprises people. Some fish, shrimp, and gelatinous organisms are partially or almost completely transparent. It functions as camouflage. Without strong light, transparent tissue becomes difficult to see. This adaptation begins appearing well before the deepest zones. It is one of the first visual clues that the environment is shifting away from the brightly lit world above. Sound behaves differently underwater compared with air. It travels faster and farther. That property becomes increasingly important as light decreases. Some fish produce clicks, grunts, or pulses. Marine mammals use echolocation. Even in mid-depth zones, acoustic communication starts playing a larger role. Humans rarely perceive this underwater soundscape directly, but instruments reveal a surprisingly active acoustic environment. Feeding strategies shift gradually. Surface ecosystems often rely heavily on photosynthesis. Phytoplankton converts sunlight into energy, supporting food chains that extend upward. Slightly deeper zones still benefit from this productivity, but the further down you go, the more organisms depend on falling organic material. Dead plankton, waste products, fragments of plants and animals. This slow rain of nutrients is sometimes called marine snow. It becomes increasingly important as depth increases. Marine snow looks unremarkable at first glance. Tiny particles drifting downward, almost like dust motes in sunlight. But for many organisms, it is a primary food source. Small crustaceans, worms, and microorganisms feed on it continuously. Larger animals consume those smaller feeders. This vertical nutrient transport connects surface ecosystems to deeper ones. It also shapes body size, feeding apparatus, and behaviour. Eyes begin changing subtly. Species living just below bright surface waters often develop larger eyes relative to body size. Collecting more light becomes advantageous. Some fish have reflective layers behind the retina, improving sensitivity. Others orient eyes upward to detect silhouettes against faint surface light. These changes are gradual, not dramatic, but they mark an evolutionary response already underway. Predator-prey relationships also adapt. Ambush tactics become more common as light decreases. Countershading, where animals are darker on top and lighter below, helps reduce visibility. Silver scales can reflect surrounding light, acting as camouflage. Behavioral adaptations appear alongside physical ones. Some species remain still for long periods, conserving energy and avoiding detection. Human perception plays a role in how all this is interpreted. Divers descending for the first time often report a sense of quiet unfamiliarity even at moderate depths. Colours fade, sounds change, movement feels slower, and the surface becomes a distant shimmering ceiling. It is not yet alien, but it is clearly not the environment humans evolved to inhabit directly. Equipment makes a difference in perception. Artificial lights restore colour temporarily. Cameras with filters adjust contrast, but these tools can distort context. A brightly lit fish against dark water may look more dramatic than it actually appears to other marine organisms adapted to low light. Understanding this helps avoid misinterpreting visual impressions. Buoyancy control becomes critical for divers and many marine animals. Slight depth changes alter pressure enough to affect gas volumes. Fish adjust swim bladders carefully. Marine mammals rely on lung compression. Submarines use ballast systems. This constant adjustment is part of life below the surface, even before reaching great depths. Another observation involves time perception underwater. Without familiar visual cues like horizon lines or sky brightness, some people report losing track of time more easily. Marine animals obviously do not measure time the way humans do, but circadian rhythms still exist. Vertical migrations often follow day-night cycles tied to surface light levels, even when animals themselves remain deeper. Biological diversity increases in some mid-water zones. Transitional habitats can support both surface-associated species and deeper specialists. That overlap creates complex ecosystems. It is one reason marine biology remains an active field of research. Each depth band offers slightly different conditions, encouraging niche specialization. Technology has allowed more detailed observation of these transitional layers. Remotely operated vehicles with sensitive cameras can hover quietly, observing natural behavior. Earlier exploration methods sometimes disturbed animals before observation. Improved tools reveal more subtle interactions, making the gradual shift from familiar to unfamiliar clearer. There is also a sensory adjustment component. Humans entering water experience muffled hearing, altered vision, temperature changes and buoyancy shifts simultaneously. Even shallow immersion can feel unusual. That sensory recalibration likely contributes to the impression that underwater environments are inherently strange. Chemical gradients exist too. Oxygen levels, salinity, nutrient concentrations and dissolved gases vary with depth. Some species cluster along these gradients. Slight chemical differences can determine habitat suitability. These invisible boundaries are as important as physical ones. As depth increases further, the cumulative effect of all these gradual changes becomes more obvious. Light weakens noticeably. Colours flatten. Movement patterns shift toward efficiency. Organisms begin showing features that prioritize survival under limited energy conditions. The transformation is not abrupt, but continuous. It is worth emphasizing that none of this is random. Evolutionary pressure shapes each adaptation. Features that seem unusual to humans often represent precise solutions developed over millions of years. Efficiency, energy conservation, and sensory optimization dominate design. The psychological transition matters too. Observers watching footage from increasing depths often move from recognition to curiosity to mild unease. Familiar fish give way to species with proportionally larger eyes, then to gelatinous forms, then to creatures using light production instead of relying on sunlight. That progression helps explain why the deepest zones eventually feel so unfamiliar, and as sunlight continues fading further below, that gradual dimming sets up the next major environmental shift. Eventually there comes a point where natural daylight barely reaches at all, and that threshold fundamentally changes how life functions, how ecosystems operate, and why the deepest parts of the ocean end up looking the way they do. If you were to stand at the edge of the ocean on a bright afternoon and look out across the water, it might seem as though sunlight fills it completely. The surface sparkles, waves flash silver and blue, and everything appears open and illuminated. It is easy to assume that light simply continues downward in the same generous way. But water does not behave like air. The moment sunlight strikes the ocean, a process begins that steadily removes it, layer by layer, until almost nothing remains. Sunlight is made up of different wavelengths, which we perceive as colours. Each wavelength carries a different amount of energy and interacts with matter differently. When light enters water, it does not travel freely. Water molecules absorb certain wavelengths very efficiently. Red light, which has a longer wavelength, disappears first. In clear ocean water, red can be mostly gone within the first few meters. That means that if you took a bright red object and lowered it just a short distance beneath the surface, it would quickly appear dull, then brownish, then almost black. Orange and yellow follow not long after. Greens penetrate farther, and blue travels the deepest, which is why deep water appears blue from above. Blue light has a shorter wavelength that interacts less strongly with water molecules, allowing it to pass farther before being absorbed. But even blue does not last indefinitely. By the time you reach a few hundred meters in most open ocean environments, natural sunlight is extremely faint. Beyond roughly 1,000 meters, depending on water clarity, it is effectively gone. This rapid disappearance of light is not only about absorption, scattering plays a role as well. Water is rarely pure. It contains microscopic particles, plankton, organic debris, and dissolved substances. When light encounters these particles, it scatters in different directions. Some of it reflects upward, some diffuses sideways. Very little continues straight downward. The result is a steady weakening of intensity as depth increases. The clarity of water matters greatly. In coastal regions where sediment and plankton concentrations are high, light fades even faster. In very clear open ocean water, sunlight may penetrate slightly deeper, but the overall pattern remains the same. Compared with air, which allows light to travel long distances with minimal loss, water is an efficient filter. This filtering has immediate biological consequences. Photosynthesis depends on sunlight. Phytoplankton, microscopic organisms that form the base of marine food webs, require sufficient light to convert carbon dioxide and nutrients into organic matter. The zone where photosynthesis can occur is called the photic zone. Its depth varies, often ranging from about 50 meters in murky coastal water to around 200 meters in very clear ocean regions. Below that, photosynthesis becomes impossible because light intensity falls below the minimum threshold required. That boundary is critical. Above it, ecosystems are driven by direct solar energy. Below it, life must rely on energy produced elsewhere. The rapid loss of light creates a sharp ecological divide. Animals that feed on phytoplankton, or the organisms that eat them, must either stay within the photic zone or develop strategies to access food drifting down from above. Even before light fully disappears, its reduction changes how organisms perceive their surroundings. Colours lose meaning. Vision becomes less reliable. Contrast diminishes. In shallow reefs, fish often display bright colours for communication or camouflage among corals. Deeper down, such coloration offers little advantage because the wavelengths needed to display those colours no longer exist. This is one reason many midwater species appear silver, black, or red. Red looks black in blue-dominated light, providing effective camouflage. The weakening of light also alters predator-prey dynamics. In bright conditions, visual detection dominates. As light fades, silhouettes become more important than detailed colour recognition. Some fish develop upward-facing eyes to detect faint outlines of prey against the residual glow from above. Others develop highly sensitive retinas capable of detecting extremely low light levels. Eventually, even that faint glow vanishes. Beyond the reach of sunlight lies the aphotic zone, a region of perpetual darkness. No sunrise, no sunset, no shifting shadows. Only the occasional flash of bioluminescence from organisms that generate their own light. This permanent darkness is one of the main reasons the deepest parts of the ocean appear so unfamiliar to us. Humans evolved in environments where light cycles define daily rhythms. Remove light entirely, and the visual landscape changes completely. It is important to understand that the disappearance of sunlight is not gradual in the way a dimmer switch feels indoors. It is more like passing through increasingly dense filters. Each meter removes a measurable fraction of intensity. Instruments lowered into the ocean record exponential decay curves, showing how quickly light intensity drops with depth. The decline is predictable and quantifiable. Temperature interacts with light penetration as well. Sunlight warms surface waters. Without light, deeper layers remain cold, often hovering just above freezing in many regions. That temperature stability contributes to slower metabolic rates in deep-sea organisms. Without solar heating, energy input into these layers is minimal. There is also a directional quality to remaining light in mid-depth zones. Most of it comes from above. That creates a faint gradient. Animals can use that gradient for orientation. Some species align vertically, maintaining position relative to light intensity. Others migrate daily, rising toward the surface at night when predation risk decreases and descending again at dawn. Cloud cover and time of day influence how much light enters the ocean. But even on the brightest day, only a small fraction penetrates beyond the upper layers. The ocean's surface reflects a portion immediately. Of the light that enters, much is absorbed within tens of meters. The deep sea receives almost none of it. From a physics perspective, water molecules vibrate in response to incoming light energy. Certain wavelengths excite molecular bonds more effectively, converting light into heat. That absorbed energy no longer contributes to illumination. Instead, it warms the water slightly before dispersing. Salinity and dissolved organic compounds also affect light transmission. Coloured dissolved organic matter, often abbreviated as CDOM, can tint water and further reduce light penetration. Regions with high river input often show shallow aphotic zones because of these dissolved substances. All of this means that the majority of the ocean exists in darkness, not because light cannot reach it at all, but because physical laws prevent it from travelling far in that medium. The ocean is deep relative to light's penetration capability. On land, light may illuminate vast distances. Underwater, it is rapidly filtered out. For organisms living below the photic zone, sunlight is irrelevant to daily survival. Their world has never included daylight. Evolution in that environment does not prioritise colour vision or surface-like behaviours. Instead, other senses dominate. Pressure resistance, energy conservation, and alternative communication systems take precedence. Human reactions to footage from these depths are influenced by our dependence on light. Darkness triggers uncertainty. When cameras illuminate a creature emerging from black water, it can feel as though something has materialised from nowhere. In reality, it was always there. Our inability to see it without artificial light creates the dramatic effect. Artificial lights used by submersibles temporarily restore visibility, but alter the natural state. Deep-sea organisms often react to sudden illumination. Some retreat, some remain still, some glow in response. The stark contrast between bright artificial beams and surrounding darkness amplifies visual impressions. Light disappearance also influences vertical habitat boundaries. Many fish species have depth limits tied directly to light levels. Some avoid total darkness, others specialise in it. These boundaries shape biodiversity patterns across depth gradients. Interestingly, not all light below the photic zone is absent. Bioluminescence provides localized illumination. Chemical reactions within specialized organs produce light without heat. This light is often blue-green because those wavelengths travel farther in water. In a sunless environment, bioluminescence becomes a primary visual signal, but bioluminescence is not a replacement for sunlight. It is sporadic, directional, and usually brief. It does not create a stable background illumination. Instead, it punctuates darkness with flashes, glows, and pulses. That patchy light environment further shapes visual systems and behaviour. Another factor involves human comparison with outer space. When people see footage from deep-sea zones devoid of sunlight, they often compare it to space exploration. Both environments are dark, high pressure in different ways, and inhospitable without technology. This comparison reinforces the perception of alienness. Yet unlike space, the deep ocean is filled with life. Darkness does not mean emptiness. It simply means that energy sources differ. Instead of solar input, many deep ecosystems rely on organic material drifting downward, or in certain areas, chemical energy from hydrothermal vents. The quick loss of sunlight establishes the environmental foundation for everything that follows. Once solar energy is no longer directly available, food webs restructure. Visual cues fade. Physical conditions stabilize into cold, dark, high-pressure consistency. Organisms that survive there reflect those constraints. As depth continues increasing, pressure becomes the dominant physical challenge, building steadily with every meter. Without sunlight to warm or illuminate, and with immense weight from above, life adapts in ways that can appear unusual to surface observers. That mounting pressure shapes body composition, movement, and internal chemistry in ways that further contribute to the distinctive appearance of deep-sea organisms. If you have ever dived to the bottom of a swimming pool and felt that slight tightening in your ears, that was pressure making itself known. It was mild, temporary, and easily relieved by surfacing again. But that small sensation hints at something far more powerful happening continuously in the deep ocean. Pressure increases steadily with depth, and unlike sunlight, which fades gradually until it disappears, pressure never stops increasing as long as water continues above you. It becomes one of the most decisive forces shaping how life looks and functions far below the surface. Water is heavy. A single cubic metre weighs roughly a metric ton. Stack kilometres of that above any point in the ocean, and the weight becomes enormous. Every 10 metres of depth adds about 1 atmosphere of pressure, roughly the same pressure we experience at sea level from the air above us. At 1,000 metres, pressure is about 100 atmospheres. In the deepest ocean trenches, it can exceed 1,000 atmospheres. That is the equivalent of several tons pressing on every square centimetre. Humans are not built for those conditions. Without specialised equipment, the human body cannot tolerate such pressure. Air-filled spaces in the body compress, gases dissolve into tissues, and structural damage occurs. Marine organisms, however, do not experience pressure as an occasional stress. For them, it is a constant environmental parameter present from birth. Evolution has shaped their bodies accordingly. One of the first adaptations involves eliminating or minimizing gas-filled cavities. Surface fish often use swim bladders, gas-filled sacs that help control buoyancy. At extreme depths, maintaining gas volumes becomes difficult because pressure compresses gases dramatically. Many deep-sea fish either lack swim bladders or have modified buoyancy systems relying more on lipids, gelatinous tissue, or reduced skeletal density. This allows them to remain neutrally buoyant without relying on compressible gas. This shift affects overall body structure. Bones may be less dense. Muscles may contain higher water content. Some deep-sea organisms appear soft or gelatinous compared with surface species. That appearance is not a flaw. It reflects efficiency under pressure. Rigid structures are not always advantageous when immense external force is constant. Flexible tissues distribute stress more evenly. Pressure also influences cellular chemistry. Proteins, enzymes, and membranes must function under conditions that would disrupt typical surface biochemistry. High pressure can alter molecular interactions, potentially interfering with metabolic processes. Deep-sea organisms produce specialized molecules, sometimes called piecelites, that stabilize cellular components under pressure. These biochemical adjustments allow normal cellular activity to continue despite extreme external force. Temperature and pressure often interact. Deep waters are usually cold, which already slows chemical reactions. High pressure can further modify reaction rates. Organisms compensate through enzyme adaptations that remain efficient in those conditions. These enzymes often differ structurally from their shallow water counterparts, reflecting long evolutionary fine-tuning. Reproduction must account for pressure as well. Eggs, larvae, and reproductive tissues must remain stable throughout development. Some species produce buoyant eggs that drift upward into slightly less extreme environments before hatching. Others complete their entire life cycle at depth, with reproductive systems adapted specifically for high-pressure stability. Movement patterns are shaped by pressure indirectly. Because buoyancy control relies less on gas, swimming mechanics differ. Many deep-sea animals move slowly, conserving energy. Rapid movement is metabolically expensive and less necessary where predator density may be lower or encounters less frequent. Slow cruising, hovering, or drifting become common strategies. Feeding adaptations follow similar logic. Food scarcity in deep environments encourages opportunistic feeding. Large mouths, expandable stomachs, and flexible jaw structures appear frequently. Pressure-resistant cartilage and connective tissue allow these feeding mechanisms to operate without structural failure. Interestingly, pressure itself is not usually perceived by deep-sea organisms the way humans feel it. Because their internal pressure matches the external environment, there is no compression gradient across tissues. Problems arise primarily when pressure changes rapidly. That is why bringing deep-sea organisms to the surface can cause visible deformation. Their bodies evolved to function at depth, not under lower pressure. Submersibles and remotely operated vehicles used by scientists must be engineered to withstand the same forces. Thick, pressure-resistant hulls, specialized materials, and careful design prevent collapse. Early deep-sea exploration faced serious technical challenges because materials capable of surviving those pressures were not always available. The consistency of pressure in deep environments contributes to ecological stability. Unlike surface waters, which experience weather-driven turbulence, temperature swings, and seasonal variation, deep waters change slowly. That stability allows certain species to develop long lifespans and slow growth rates. Some deep-sea fish live decades, even centuries, partly because metabolic rates remain low and environmental conditions fluctuate little. Pressure also influences sensory systems. Sound travels efficiently underwater regardless of depth, but pressure can affect the sensitivity of sensory organs. Some fish possess pressure-detecting systems that help them maintain depth orientation or detect movement in surrounding water. Chemical solubility changes under pressure. Gases dissolve differently, and certain compounds remain stable only at high pressures. Hydrothermal vent ecosystems, which we will discuss later, rely heavily on pressure-dependent chemical reactions. Life there is built around chemistry that would not function the same way at the surface. Another consequence involves decomposition. Organic material sinking from above encounters increasing pressure and decreasing temperature. These conditions slow microbial breakdown somewhat, allowing particular organic matter to travel farther downward. That slow nutrient rain supports deep ecosystems despite the absence of direct photosynthesis. Human perception of pressure is limited without instruments. We cannot see it directly. We infer it through its effects. That invisibility is why pressure can be described as an invisible sculptor. It shapes anatomy, behavior, chemistry, and ecology without being visually obvious in footage or photographs. Deep-sea creatures sometimes look unusual, not because pressure distorts them, but because pressure has selected for forms that function best under those conditions. Soft-bodied organisms may be perfectly adapted, not fragile. Large eyes in some species compensate for low light, but eye structure must also withstand pressure. Internal fluids, supportive tissues, and protective membranes reflect those dual demands. There are also threshold depths where specific adaptations become more common. As pressure passes certain levels, swim bladders become rare, skeletal density decreases, and biochemical stabilizers increase. These transitions align with ecological zones defined partly by pressure gradients. Exploration technology continues improving our understanding. Modern sensors measure pressure precisely, allowing correlation between depth, species distribution, and physiological adaptation. Earlier assumptions sometimes underestimated how specialized deep-sea organisms truly are. Interestingly, some organisms migrate vertically despite pressure differences. Certain species ascend hundreds of meters nightly to feed, then descend again by day. Their physiology accommodates those changes gradually, avoiding rapid decompression effects. Studying these migrations provides insight into pressure tolerance mechanisms. Marine mammals offer a contrasting example. Whales and seals dive deeply, but are not permanently adapted to those pressures. They have flexible rib cages, collapsible lungs, and oxygen storage adaptations that allow temporary descent. But they must return to the surface regularly. Deep-sea fish, by contrast, remain continuously at depth. There is also an evolutionary timescale component. Pressure adaptation does not occur quickly. It reflects millions of years of gradual change. Lineages moving deeper over evolutionary time accumulate structural and biochemical modifications that become permanent traits. Environmental disturbances at depth, such as underwater landslides or volcanic activity, can temporarily alter pressure locally. Species adapted to stable conditions may struggle with sudden changes. However, such events are relatively rare compared with surface weather variability. Human activities like deep-sea mining introduce new variables. Equipment operating at depth must withstand pressure, and disturbances can affect sediment layers, chemical gradients, and biological communities that evolved under stable conditions. Understanding pressure-related ecology helps assess potential impacts. Another point involves acoustic research. Pressure affects sound propagation slightly, influencing how sonar signals travel. Scientists use these properties to map seafloor structures and detect biological activity. Psychologically, when people learn about the magnitude of deep ocean pressure, it often reinforces the perception that those environments are extreme, even hostile. That reaction contributes to the sense that organisms living there must be unusual. In reality, they are simply well adapted. Educational outreach sometimes uses comparisons to make pressure relatable. For example, describing a small area experiencing the weight of several elephants helps illustrate scale. These comparisons are imperfect but convey magnitude. Scientific sampling methods must account for pressure preservation. Some research uses pressure-retaining containers that keep organisms at near native pressure during retrieval, allowing more accurate study of physiology and behaviour. Understanding pressure adaptation also informs astrobiology. Environments on other planetary bodies, such as subsurface oceans on icy moons, may involve high-pressure conditions. Studying Earth's deep-sea life provides useful analogues. The cumulative effect of pressure on life is subtle when viewed piece by piece, but significant overall. Body composition, metabolic rates, feeding strategies, reproduction, sensory systems, and ecological interactions all reflect its influence. It is not dramatic in the sense of sudden visible transformation, but persistent, shaping life continuously. As depth increases further beyond where sunlight fades and pressure intensifies, organisms rely less on vision entirely. Darkness becomes complete, and alternative ways of navigating, communicating, and finding food take precedence. That transition into permanent darkness explains why many deep-sea creatures exhibit features specifically designed for life without light. By the time you descend far enough that sunlight no longer reaches at all, something fundamental changes. It is not just that the environment becomes dim, it becomes permanently dark. There is no sunrise, no faint twilight, no seasonal variation in daylight. The darkness in these regions is not temporary or cyclical, it is constant. For the organisms that live there, darkness is not an absence. It is the default condition under which every sense, every movement and every survival strategy has evolved. When humans imagine total darkness, it often carries a sense of uncertainty. We depend heavily on vision. Our architecture, transportation, communication, and daily routines assume reliable light. Remove it, and orientation becomes difficult. In the deep ocean, however, countless species have never relied on sunlight. Their ancestors adapted gradually as lineages moved into deeper habitats over evolutionary time. Over millions of years, natural selection shaped bodies that function efficiently without ever seeing daylight. One of the most noticeable changes in some deep-sea creatures is the modification of eyes. Interestingly, the pattern is not uniform. Some species have extremely large eyes relative to body size, others have very small eyes, and some have none at all. The difference depends on ecological niche and depth. In the upper parts of the aphotic zone, faint residual light from above may still exist, along with bioluminescent signals from other organisms. In that environment, large, highly sensitive eyes are useful. These eyes often contain reflective layers behind the retina, increasing the chance that scarce photons trigger visual responses. Some species have tubular eyes that point upward, maximizing detection of silhouettes against faint background glow. Deeper still, where even that minimal light is absent, eyes may become reduced. Maintaining complex visual organs requires energy. If vision offers no advantage, natural selection favours individuals that allocate resources elsewhere. Over time, eyes shrink, lose complexity, or disappear entirely. In certain deep-sea fish and invertebrates, eye sockets remain as vestigial structures, evidence of ancestors that once depended more on sight. The loss of vision does not mean sensory deprivation. Other senses become highly refined. Many fish possess lateral line systems that detect subtle water movements. In darkness, detecting the faint displacement caused by another organism can mean the difference between finding food and becoming food. These systems are often more sensitive in deep species. Chemical sensing also becomes crucial. Water carries dissolved molecules efficiently. Some deep-sea animals can detect trace chemical cues from potential prey, or mates at remarkable distances. Antenna-like appendages in crustaceans or elongated sensory barbels in fish function as chemical detectors in a world where visual signals are limited. Electric field detection is another adaptation found in certain groups. Weak electrical impulses generated by muscle activity can be sensed by specialized receptors. In darkness, this provides additional information about nearby organisms. Body shapes in eternal darkness often reflect energy efficiency. Many deep-sea creatures have elongated forms, reduced muscle mass, and lightweight skeletons. Without light-driven productivity, food is scarce. Energy conservation becomes critical. Fast swimming is rare compared with surface environments. Slow, deliberate movement dominates. Some species develop exaggerated feeding structures. Large mouths and expandable stomachs are common. When prey is unpredictable, the ability to consume large meals opportunistically is advantageous. There are fish capable of swallowing prey nearly their own size. From a surface perspective, such proportions can appear disproportionate or unsettling, but in context they are logical. Bioluminescence becomes a primary source of visible light in these environments. Many deep-sea organisms produce light through chemical reactions involving luciferin and luciferous compounds. This light is usually blue-green because those wavelengths travel farthest in water. Bioluminescence serves multiple purposes. attracting prey, signalling to mates, camouflage through counter-illumination, or startling predators. Counter-illumination is particularly interesting. Some midwater fish have light-producing organs along their undersides. By matching the faint light from above, they reduce their silhouette when viewed from below. Even in near darkness, subtle light differences matter. Communication in darkness often relies on patterns of flashes. Some species produce species-specific light sequences, functioning almost like coded signals. Others use light lures that mimic prey movement. The anglerfish is a well-known example, though it represents only one of many bioluminescent strategies. Reproductive adaptations can also appear unusual. In certain deep-sea anglerfish species, males are much smaller than females. Upon locating a female, a male may attach permanently, fusing tissues and sharing circulatory systems. This ensures reproductive access in an environment where encounters are rare. To human observers, this arrangement can seem extraordinary, but it reflects adaptation to low population density and vast habitat space. Transparency remains useful in some zones, though less so in absolute darkness. In midwater darkness where bioluminescence occurs, transparency can still reduce visibility. Some gelatinous organisms remain nearly invisible except when illuminated by artificial light. Metabolic rates in these environments are typically low. Cold temperatures and limited food supply encourage slow growth and extended lifespans. Some deep-sea fish exhibit longevity far exceeding comparable shallow species. Slow development aligns with stable environmental conditions. Coloration often shifts toward black, red, or absence of pigmentation. Black absorbs available light, minimizing reflection. Red appears black under blue-dominated light. Pigment reduction can conserve energy if coloration offers little benefit. Another adaptation involves pressure-resistant cellular membranes. In eternal darkness, depth often correlates with extreme pressure. Cellular components must remain stable under those conditions. Specialized fatty acids and structural proteins maintain membrane flexibility and enzyme function. Behavioral patterns differ significantly from surface rhythms. Without sunlight, circadian cycles may rely on other cues, possibly tied to vertical migration of prey species or subtle environmental gradients. Some species may not follow daily cycles at all. Hunting strategies often rely on patience. Sit-and-wait predation conserves energy. Ambush from below, where prey silhouettes against faint light, is common in upper dark zones. Deeper species may rely more on detecting vibrations or chemical signals before making short, efficient strikes. The absence of plants changes habitat structure. Coral reefs and kelp forests depend on light. In deep darkness, habitat complexity arises from geological features like ridges, trenches, and hydrothermal vents. Some organisms attach to hard substrates, while others remain free-floating in mid-water. Human reactions to footage from these depths are shaped by unfamiliarity with such sensory priorities. Large eyes, glowing organs, oversized jaws, and elongated bodies challenge surface-based expectations of proportion and symmetry. Yet within their environment, these features are balanced and functional. The consistency of darkness also reduces seasonal variation. Surface ecosystems respond to day-length changes and temperature shifts. Deep-sea environments remain comparatively stable year-round. That stability influences reproduction timing, growth rates, and migration patterns. Research into deep-sea darkness has expanded significantly with improved camera technology, capable of capturing low-light conditions without overwhelming organisms with artificial beams. Infrared-sensitive equipment allows more natural observation. Interestingly, some species that appear delicate are structurally robust under pressure. Their gelatinous composition distributes force evenly. Removed from depth, they may appear collapsed or misshapen, reinforcing misconceptions about fragility. There is also evidence of vertical migrations even in darkness. Some species move hundreds of meters nightly to feed on organisms that ascend from deeper layers. These migrations represent one of the largest daily movements of biomass on the planet. Predator-prey arms races continue in darkness. Sensory acuity improves incrementally generation by generation. Bioluminescent deception evolves in response to detection strategies. The absence of sunlight does not mean reduced complexity. It simply shifts the parameters of adaptation. The idea of eternal darkness can sound extreme, but it is normal for the majority of Earth's living space. Most ocean volume lies beyond sunlight's reach. Life there is not an exception. It is a dominant mode of existence on the planet. As darkness becomes absolute, bioluminescence stands out more sharply. Those self-generated lights punctuate the black environment in ways that look almost theatrical when captured on camera. Understanding how and why organisms create light reveals another layer of adaptation that contributes significantly to the perception that deep-sea life appears otherworldly. Once sunlight disappears completely, darkness becomes the background condition rather than an occasional inconvenience. Yet the deep ocean is not visually empty. There are flashes, glows, pulses, slow shimmering signals, brief sparks that vanish almost as soon as they appear. This light does not come from the sun. It comes from the organisms themselves. Bioluminescence, the ability of living creatures to produce light chemically, becomes one of the defining features of deep-sea ecosystems. At first, the idea of animals generating their own light can sound unusual, but chemically it is quite straightforward. Most bioluminescent reactions involve a molecule called luciferin and an enzyme called luciferase. When luciferin reacts with oxygen in the presence of luciferase, light is emitted. The process is efficient. Very little energy is lost as heat, which is why bioluminescence is sometimes described as cold light. This efficiency matters in environments where energy conservation is essential. Blue-green wavelengths dominate deep-sea bioluminescence. That is not random. Blue-green light travels farther through seawater than other colours. If an organism is producing light for communication, camouflage or hunting, emitting wavelengths that propagate efficiently makes evolutionary sense. Some species produce slightly different hues, but blue-green remains the most common. The purposes of bioluminescence vary widely. One of the most familiar uses is attracting prey. Glow approach what appears to be food. Glow approach what appears to be food, only to become food themselves. The strategy relies on curiosity or attraction to light in an otherwise dark environment. Defense is another major function. Some organisms release glowing clouds when threatened. This sudden burst of light can startle predators, create confusion, or illuminate the predator itself, making it more visible to its own predators. Certain shrimp eject bioluminescent secretions similar to how squid release ink. But instead of creating darkness, they create a distracting glow. Communication also plays a significant role. Species-specific flash patterns allow individuals to recognize potential mates or members of their own species. In darkness, where visual cues are limited, light signals provide a reliable method of identification. Some fish have rows of photophores, specialized light-producing organs arranged in patterns unique to their species. Counter-illumination is one of the more subtle uses. Many midwater fish and squid possess light organs along their undersides. These organs emit light matching the faint residual glow from above. When viewed from below, the animal's silhouette disappears because its underside brightness blends with the background. It is camouflage achieved by producing light rather than blocking it. Some organisms use bioluminescence to illuminate prey directly. Certain fish have forward-facing light organs near their eyes, functioning somewhat like headlights. This allows them to see potential food without relying on ambient light. The emitted light is often narrow in beam and carefully controlled to avoid attracting unwanted attention. Symbiotic relationships sometimes drive light production. In several species, the light does not originate from the animal's own cells, but from bacteria living in specialized organs. The host provides nutrients and protection. The bacteria produce light. This partnership benefits both parties. The host gains illumination capability, and the bacteria gain a stable habitat. Bioluminescent bacteria exist independently as well. When disturbed, they can cause glowing water effects sometimes observed near shorelines at night. In the deep sea, bacterial luminescence contributes to ambient light levels in certain microenvironments. Energy cost remains a factor. Producing light requires metabolic resources. Organisms balance the benefits of signalling or camouflage against energy expenditure. Efficient chemical pathways make bioluminescence viable even where food is limited. Behavioral timing matters. Some species emit light continuously at low intensity. Others flash intermittently. Flashing conserves energy and reduces detectability by predators that might track constant light sources. The patterns themselves can convey information about species identity, readiness to mate, or territorial presence. Human observers often find bioluminescence visually striking because it contrasts sharply with darkness. Cameras capture bright points against black backgrounds, enhancing dramatic effect. But for organisms accustomed to these conditions, the light is simply part of normal sensory input. Research into deep-sea light production has practical applications. Scientists study luciferin-luciferase systems for medical imaging, environmental monitoring, and biotechnology. These natural chemical reactions provide templates for sensitive detection methods in laboratories. There is also a mechanical dimension. Some organisms can control light intensity or direction using reflective tissues, shutters, or muscular adjustments. This allows rapid modulation of signals. It is not unlike adjusting a flashlight beam, except the system is biological. Predators sometimes exploit bioluminescent signals. If prey species use specific flash patterns, predators may learn to recognize and track them. This creates evolutionary feedback loops. Prey refine signals, predators refine detection. Over time, complexity increases. Another interesting phenomenon involves synchronized flashing. Certain species coordinate light emissions in groups, creating wave-like patterns. The function is not always fully understood, but may involve mating coordination or predator confusion. Light sensitivity evolves alongside light production. Deep-sea eyes often contain pigments optimized for blue-green wavelengths. Neural processing pathways emphasize motion detection and contrast rather than detailed color discrimination. Some species remain completely non-luminescent despite living among glowing organisms. Their strategy often relies on stealth, avoiding both emitting light and reflecting it. Matte skin textures reduce stray reflections. The distribution of bioluminescent organisms is not uniform across depths. It tends to peak in mid-water zones where residual light from above interacts with darkness below. Farther down, where even bioluminescent interactions become less frequent, other sensory strategies dominate. Environmental disturbances can trigger mass luminescence. Movement of water by submersibles or large animals sometimes causes widespread glowing responses from microorganisms. This can create the impression of stars appearing in black water. Bioluminescence also assists in vertical orientation. Organisms can gauge relative depth by light intensity gradients, whether from residual surface light or nearby bioluminescent activity. The evolutionary origin of bioluminescence appears multiple times across unrelated lineages. Fish, squid, crustaceans, jellyfish, worms, and bacteria all independently evolved light-producing capabilities. This repeated emergence suggests strong adaptive value under certain environmental conditions. There are variations in light duration. Some flashes last fractions of a second, others glow steadily for minutes. Duration often correlates with function. Communication signals may require recognizable patterns, while defense flashes may prioritize sudden brightness. Temperature influences reaction efficiency. Cold deep-sea conditions affect chemical kinetics. Bioluminescent systems have adapted to remain functional at low temperatures. Human exploration has revealed that bioluminescence is far more widespread than once thought. Estimates suggest a majority of deep-sea organisms possess some form of light production. It is not an occasional curiosity but a central ecological feature. Cultural reactions to glowing sea life often involve comparisons with science fiction imagery. Yet the phenomenon predates human imagination by millions of years. It is a natural solution to living without sunlight. There are also seasonal influences in upper dark zones tied to surface productivity cycles. Increased organic matter from plankton blooms can support higher densities of bioluminescent organisms temporarily. Predation risk sometimes depends on whether emitting light makes an organism more visible. Some species produce extremely faint glows detectable only by sensitive eyes, balancing communication with stealth. Scientific observation continues improving as low-light cameras become more sensitive. Earlier expeditions sometimes overwhelmed animals with bright lights, altering behaviour. Modern equipment allows more natural study. Understanding bioluminescence contributes to broader ecological knowledge. It helps map species distributions, identify behavioural patterns, and infer food web interactions. The presence of self-generated light in a permanently dark environment highlights how life adapts to sensory limitations. Instead of relying on external illumination, organisms create their own signals, turning darkness into a communication medium rather than a barrier. And as these glowing organisms drift, hunt, signal, or defend themselves in the black water, their bodies often reflect additional adaptations beyond light production. Some appear almost transparent, others look oversized or oddly proportioned. These physical designs continue the pattern of life, adjusting to conditions that differ greatly from the sunlit world above. If you watch enough deep-sea footage, there comes a moment when certain animals stop looking like what most people instinctively classify as animals. Some appear gelatinous, almost shapeless. Others drift slowly with little visible effort. A few seem nearly transparent, as if only partially there. From a surface perspective, these organisms can look fragile, unfinished, or even artificial. Yet they are not struggling or defective. They're often perfectly adapted to conditions that reward energy efficiency, pressure tolerance, and minimal structural overhead rather than speed or strength. One of the main reasons many deep-sea creatures look this way is the scarcity of energy. In sunlit waters, photosynthesis drives abundant food chains. Plankton blooms feed fish feed larger predators, and energy circulates actively. In deep environments where sunlight never reaches, food arrives slowly. Dead organisms sink from above, waste particles drift downward. Occasionally larger carcasses fall, providing temporary abundance. But overall energy input is limited. Organisms that waste energy on unnecessary tissue, heavy skeletons, or constant motion tend not to thrive. Gelatinous bodies solve several problems at once. They require less energy to build compared with dense muscle and bone. They often match the density of surrounding water closely, allowing neutral buoyancy without active swimming. This means an organism can remain suspended with minimal effort. The result is a drifting lifestyle that conserves calories. Jellyfish, comb jellies, siphonophores, and various deep-sea larvaceans exemplify this approach. Their tissues consist largely of water, supported by thin structural proteins. Under pressure, this composition distributes force evenly. What appears delicate in surface conditions can be entirely stable at depth. When brought upward rapidly, however, reduced pressure can distort their shape, contributing to the impression that they are fragile or incomplete. Transparency is another adaptation frequently seen in midwater darkness. Transparent tissues reduce visibility. Without strong light, a nearly invisible organism becomes difficult to detect. Predators relying on silhouettes or faint reflections may overlook them entirely. Maintaining transparency requires minimizing pigments, complex structures, and opaque organs. Internal organs often cluster centrally, leaving outer tissues clear. Even when not fully transparent, Many deep-sea animals exhibit muted coloration. Black, deep red, or colourless bodies dominate. These colours minimise reflectivity. Red appears black in blue-filtered deep water, making it effective camouflage. Some shrimp fish and squid species use this strategy extensively. Muscle reduction is common where rapid pursuit is unnecessary. Instead of fast chases, many deep-sea predators rely on ambush tactics. Remaining still until prey approaches conserves energy. When movement occurs, it is often short, deliberate and efficient rather than sustained. Skeletons may also differ significantly from surface species. Reduced calcification lowers metabolic cost. Flexible cartilage can replace rigid bone in certain structures. Some fish have lightly mineralized skeletons that function well under constant pressure, but would seem unusually soft at the surface. Buoyancy mechanisms often involve lipids instead of gas. Oils remain incompressible under pressure. Storing lipids allows stable buoyancy without swim bladders. These oils can also serve as energy reserves, useful when meals are unpredictable. Another feature that contributes to the barely alive appearance is slow metabolism. Cold temperatures combined with limited food availability encourage reduced metabolic rates. Heart rates, digestion speed, and overall activity remain low. Movements appear unhurried because rapid activity offers little advantage in that environment. Longevity often increases under these conditions. Some deep-sea fish species live decades or longer. Slow growth and delayed maturity align with stable environments, where sudden population booms are rare. Sensory structures sometimes look disproportionate. Large eyes in dim zones, elongated antennae in crustaceans, or sensitive lateral lines may dominate body proportions. These features prioritize detection over locomotion. Feeding apparatus can appear exaggerated. Wide jaws, extendable stomachs, or recurved teeth reflect opportunistic feeding strategies. A rare prey encounter must be maximized. The structure may look excessive compared with surface fish, but it aligns with energy economics. Skin texture often differs as well. Many deep-sea organisms lack heavy scales. Smooth, flexible skin reduces energy costs associated with scale production and maintenance. It also improves pressure distribution. Some species exhibit extreme minimalism. Certain worms, amphipods, and small fish reduce structures to essentials: sensory input, feeding apparatus, reproductive capability, and minimal locomotion. Anything beyond that may represent unnecessary metabolic expense. Hydrodynamics still matter, even with slow movement. Streamlined shapes reduce drag. However, the optimization often favors drifting efficiency rather than speed. Rounded or elongated gelatinous forms reflect this balance. Reproductive strategies can influence appearance. Some species invest heavily in fewer offspring, producing large eggs with energy reserves. Others release vast numbers of small eggs. Body structure reflects these choices indirectly through energy allocation. There is also the matter of developmental stages. Some organisms retain larval characteristics into adulthood, a phenomenon called neoteny. Larval forms often have simpler bodies, which can appear unusual when retained permanently. Pressure influences internal fluid balance. High external pressure compresses gas but not liquids. Maintaining consistent internal fluid composition supports cellular stability. Some deep-sea species have high concentrations of specific solutes that stabilize proteins under pressure. Behavioral stillness contributes to perception. An organism that barely moves may appear lifeless at first glance. Cameras capturing slow drifting motion reinforce that impression. In reality, minimal movement is often intentional energy conservation. Another factor involves limited structural damage risk. In calm, deep waters, there is less turbulence compared with surface zones. Delicate appendages face fewer mechanical stresses. This allows finer sensory structures to evolve. Microbial symbiosis sometimes shapes body form. Certain deep-sea invertebrates host bacteria that assist with nutrition. Specialized tissues house these microbes, influencing external morphology. When deep-sea animals are captured and brought to the surface, decompression can cause swelling, tissue rupture, or collapse. These artifacts contribute to misconceptions about their natural form. Pressure-retaining sampling methods have improved accuracy in recent research. Technological imaging advances now allow observation in situ, meaning at natural depth and pressure. This reveals more accurate behaviour and appearance, often less distorted than earlier specimens suggested. Public perception remains influenced by dramatic imagery. Transparent fish with visible internal organs, gelatinous drifters illuminated against black water, or slow undulating movements all contrast with expectations shaped by land animals. Educational framing helps contextualize these appearances. Once viewers understand the energy limitations, pressure conditions, and darkness involved, the designs become more logical. There is also an aesthetic shift over time. Researchers who spend years studying these organisms often describe them as elegant or efficient rather than strange. Familiarity reduces the initial sense of alienness. These body forms also remind us that life does not follow a single template. Conditions determine design. Where sunlight, warmth, and abundant food exist, active bodies dominate. Where darkness, cold, and scarcity prevail, minimalism often wins. The perception that something barely looks alive often reflects human bias toward movement, colour, and complexity. Remove those cues, and the brain hesitates to categorize what it sees. Yet despite their subdued appearance, deep-sea organisms maintain complex ecological relationships. Predation, competition, reproduction, and symbiosis continue just as actively, even if visually understated. As exploration continues, new species keep appearing that challenge surface expectations further. Some combine transparency with bioluminescence. Others exhibit extreme elongation or unusual sensory arrangements. Each discovery expands understanding of how flexible biological design can be. And beyond these minimalistic body forms, another pattern becomes noticeable the deeper observations go. Some animals grow unexpectedly large, while others remain remarkably small, and certain species display body proportions that seem exaggerated compared with shallow water relatives. These variations add another layer to why the deep ocean can appear visually unfamiliar. As more observations accumulated from deep-sea expeditions, scientists began noticing a pattern that did not always match expectations formed from surface ecosystems. Some animals living at depth were unusually large compared with their shallow water relatives, while others seemed remarkably small or unusually delicate. At the same time, transparency, elongated appendages, exaggerated jaws, and body proportions that seemed unbalanced by surface standards appeared repeatedly. These traits are not random. They reflect consistent environmental pressures acting over long, evolutionary timescales. Gigantism is one of the most striking features. The term does not imply that every deep-sea organism is large. Many are quite small, but certain groups, particularly crustaceans, cephalopods, and some fish, exhibit larger than expected sizes. Giant isopods, for example, resemble oversized pillbugs, sometimes exceeding 30 centimeters in length. Giant amphipods, deep-sea squid species, and some jellyfish also illustrate this trend. Several factors likely contribute to deep-sea gigantism. Cold temperatures slow metabolism, which can extend lifespan. Longer lifespans provide more time for growth. Stable environmental conditions reduce the need for rapid reproduction, allowing energy investment in gradual size increase. Predation pressures may differ as well, sometimes favouring larger size as protection. Oxygen availability plays a role too. Cold water can hold more dissolved oxygen than warm water. Higher oxygen availability may support larger body sizes in some species, though this effect varies depending on habitat depth and local conditions. Food availability, while generally limited, occasionally arrives in large pulses. A whale carcass sinking to the seafloor can sustain a community for years. Species capable of exploiting such episodic abundance may benefit from larger size, which allows energy storage. But gigantism is not universal. In many cases, the opposite trend appears. Some deep-sea organisms are extremely small. Reduced size lowers energy requirements, which can be advantageous where food is unpredictable. The coexistence of gigantism and miniaturization reflects diverse survival strategies rather than a single evolutionary direction. Transparency, which appeared earlier in transitional zones, continues to play a role deeper down, particularly in mid-water habitats. Transparent shrimp, larval fish, and gelatinous organisms minimize visibility by allowing light to pass through their tissues. Even in darkness, occasional bioluminescent flashes can reveal silhouettes. Transparency reduces that risk. Maintaining transparency requires specific tissue composition. Pigments must be minimized. Structural proteins must be arranged to reduce light scattering. Organs often cluster centrally, leaving peripheral tissue clearer. Blood pigments may be reduced or modified in some species. Another common design feature involves elongated appendages. Long antennae, trailing tentacles, or extended sensory filaments increase the probability of detecting food, mates, or environmental cues in sparse conditions. These structures may appear excessive compared with surface species, but they improve sensory reach without requiring constant movement. Jaw enlargement also appears frequently. Some deep-sea fish possess disproportionately large mouths relative to body size. Expandable ligaments allow them to engulf prey larger than their head diameter. This capability reflects opportunistic feeding. Passing up a rare meal could have serious consequences, so anatomical flexibility becomes advantageous. Teeth in these species often appear oversized or needle-like. Sharp, recurved teeth help secure prey once captured. In low-light conditions, precise targeting may be difficult, so grasping efficiency matters. Eye variation remains interesting. Some species retain very large eyes, particularly in mid-water darkness where faint bioluminescence occurs. Others reduce or eliminate eyes entirely where light offers no advantage. Both strategies reflect optimization rather than abnormality. Skin texture often looks smooth, thin, or gelatinous. Heavy armor requires energy investment. In environments with fewer mechanical hazards, lighter protective structures suffice. Some species retain protective spines or scales, but many reduce them. Coloration trends toward dark tones. Black absorbs available light, minimizing reflection. Deep red functions similarly under blue-dominated illumination. Pigment reduction can conserve metabolic resources. Buoyancy adaptations continue evolving. Oil-filled tissues, reduced skeletal density, and gelatinous composition all contribute to neutral buoyancy without relying on gas-filled cavities. Maintaining position in the water column without constant swimming conserves energy. Some species exhibit balloon-like body forms. This shape increases volume relative to mass, improving buoyancy efficiency. It may appear inflated from a surface perspective, but at depth, it represents balanced density. Another adaptation involves slow growth combined with delayed maturity. Deep-sea fish, such as orange roughy, can live well over a century. Long lifespans allow gradual size increase, but also make populations vulnerable to overfishing, because recovery rates are slow. Reproductive strategies often adjust accordingly. Fewer offspring with higher survival investment may replace large numbers of quickly produced young. This influences body energy allocation and morphology. Certain deep-sea squid display enormous eyes compared with body size. These eyes may detect faint bioluminescent signals from large predators like sperm whales. Enhanced detection provides survival advantage despite energy cost. Body elongation appears in eel-like fish species. Long, flexible bodies allow efficient slow swimming and exploration of the narrow spaces near the seafloor, or within mid-water layers. Pressure tolerance influences tissue composition indirectly. Gelatinous tissues distribute pressure evenly. Rigid structures require reinforcement to avoid damage, increasing energy cost. There are also examples of extreme morphological specialization. Some fish possess hinged skulls for wide gape feeding. Others develop luminous organs integrated into skin patterns. Certain crustaceans have elongated limbs used primarily for sensory detection rather than locomotion. Public reaction to these forms often involves surprise, because proportions differ from common land animals. Large heads, small bodies, extended appendages, or reduced eyes challenge expectations. However, these designs follow clear functional logic. Energy conservation, sensory optimization, buoyancy stability, and feeding efficiency drive morphology. Environmental stability contributes to slow evolutionary change once optimal designs emerge. Deep-sea habitats often experience less seasonal variability than surface zones. Consistent conditions favour specialization. Temperature gradients remain minimal in many deep zones, reinforcing metabolic stability. Combined with pressure constancy, this creates predictable selective pressures. Food web structure influences body size distribution. Apex predators may grow larger due to longer lifespans and episodic feeding opportunities. Detritus feeders may remain small but numerous. Technological observation improvements have clarified how these animals move and interact naturally. Earlier assumptions sometimes overemphasize fragility. Many gelatinous organisms are structurally resilient under pressure. Another design feature involves reflective surfaces. Some fish have mirror-like scales that scatter faint light, reducing detectability. This works in tandem with dark pigmentation. Sensory trade-offs remain common. Reduced vision may accompany enhanced chemical or vibration detection. Energy saved from one system supports another. Human interpretation of odd design often reflects unfamiliar environmental context. Once pressure, darkness, and food scarcity are considered, these forms become understandable. Comparisons with extraterrestrial life frequently arise in media coverage. While visually striking, these organisms evolved under Earth conditions. Their unfamiliarity stems from limited human exposure rather than alien origin. Understanding these morphological adaptations helps predict how species might respond to environmental change. Altered temperature, pressure, or nutrient input could shift selective pressures over time. There is also ongoing research into developmental biology. How genes regulate these unusual forms provides insight into evolutionary flexibility across species. Gigantism, transparency, elongation, and other design variations collectively demonstrate that life optimizes for environment rather than aesthetic familiarity. Efficiency under constraints shapes form, and as these bodies drift through darkness, communication becomes less about appearance and more about signals carried through water. Sound, vibration, and other non-visual cues begin playing increasingly important roles, further defining how deep-sea organisms interact in environments where light offers limited guidance. Once sunlight fades and visual cues lose their usefulness, other forms of communication naturally become more important. In the deep ocean, sound travels efficiently, often more reliably than light ever could. Water carries vibrations faster and over longer distances than air, which means that even subtle movements can propagate outward in ways that are meaningful to nearby organisms. This does not mean the abyss is constantly noisy. It often feels quiet by human standards. But beneath that apparent stillness, a continuous exchange of signals takes place, shaped by physics, biology, and environmental stability. Sound behaves differently underwater because water is denser than air. Vibrations move more quickly through it, roughly 4 times faster than through air. They also lose energy more slowly. This combination allows acoustic signals to travel considerable distances. Marine mammals use this property extensively. Whales, for instance, communicate across kilometers using low-frequency calls. Even in deep zones where whales visit only temporarily, those sounds can be detected by other organisms. Fish also produce sounds, though usually at higher frequencies and shorter ranges. Some contract specialized muscles against swim bladders to create drumming noises. Others grind teeth or bones together. These sounds can serve territorial purposes, mating communication, or group coordination. In darkness, where vision is limited, sound offers reliable information about nearby activity. Not all deep-sea organisms generate sound actively. Many rely instead on detecting vibrations produced by movement. The lateral line system present in most fish is particularly important. This system consists of fluid-filled canals along the body connected to sensory hair cells. Minute pressure changes in the surrounding water stimulate these cells, providing information about nearby motion. A swimming predator, drifting prey, or even water displaced by geological activity can be detected this way. Crustaceans often possess long antennae rich in mechanoreceptors. These structures pick up subtle water movements. In a world without consistent light, detecting flow patterns can help locate food, avoid predators, or find mates. Silence in the deep ocean is not absolute. There are background noises generated by geological processes such as underwater earthquakes, volcanic activity, or shifting sediment. Currents moving across the seafloor create low-frequency sound. Ice movement in polar regions can produce distant acoustic signals detectable far below. Human activity has added new acoustic elements. Ship engines, sonar, and industrial operations introduce sounds that propagate widely underwater. Some research suggests these noises may influence animal behavior, though the extent varies by species and frequency. Marine mammals use echolocation extensively. Toothed whales and dolphins emit high-frequency clicks and interpret returning echoes to map surroundings. While they typically hunt at various depths rather than permanently living in the deepest zones, their acoustic signals can penetrate dark waters effectively. Echolocation allows precise navigation without relying on light. Certain fish species may use more limited forms of active sonar-like behaviour, though not as sophisticated as marine mammals. Experimental studies suggest some fish produce clicks that may help with orientation or communication. Chemical communication complements acoustic signalling. Dissolved molecules spread through water, providing olfactory cues. Some species release pheromones indicating reproductive readiness. Others detect chemical traces of injured prey. This form of communication is slower than sound but persistent. Electrical sensing appears in some groups as well. Weak electric fields generated by muscle contractions can be detected by specialized receptors. Sharks and rays use this sense extensively in shallower environments, and related mechanisms appear in some deep species. Bioluminescence, discussed earlier, interacts with acoustic communication indirectly. Light flashes can accompany sound production or movement, providing multimodal signals. In darkness, combining sensory channels improves detection reliability. Population density influences communication strategies. In sparse environments, signals that travel farther become advantageous. Low-frequency sounds travel longer distances but carry less detail. High-frequency signals provide detail but attenuate quickly. Species balance these trade-offs based on ecological needs. The seafloor itself influences acoustics. Soft sediment absorbs sound differently than rocky substrates. Underwater topography can reflect, scatter, or channel acoustic waves. Submarine canyons sometimes act as sound pathways, extending communication range. Temperature and salinity gradients also affect sound propagation. These gradients create layers that bend acoustic waves, a phenomenon known as refraction. This can cause sound to travel farther horizontally while limiting vertical movement, depending on conditions. Scientists use hydrophones to study these soundscapes. Arrays placed at depth record natural and anthropogenic sounds. Analysis reveals patterns in animal communication, migration, and environmental change. From a human perspective, the deep ocean often seems silent because our hearing is adapted to air. Without specialized equipment, we perceive little underwater sound. This sensory limitation contributes to the impression of stillness. In reality, the abyss contains continuous low-level acoustic activity. Organisms moving, feeding, reproducing, or interacting all generate subtle vibrations. Over time, these contribute to a complex but understated sound environment. Predation strategies often incorporate acoustic stealth. Some predators move slowly to minimize vibration. Others use sudden bursts of motion only when prey is within reach. Prey species, in turn, evolve sensitivity to early vibration cues. Group coordination sometimes relies on sound. Certain fish schools maintain cohesion using acoustic signals when visual cues are insufficient. This helps reduce predation risk. Communication timing may align with vertical migrations. Many species ascend or descend daily. Acoustic signals can coordinate these movements or facilitate mate finding during migration periods. Hydrothermal vent communities, which we will explore later, generate unique acoustic signatures due to fluid flow and geological activity. Organisms adapted to those habitats may use these background sounds as orientation cues. Another interesting aspect involves pressure effects on sound perception. High pressure influences the physical properties of sensory organs. Deep-sea species exhibit structural adaptations ensuring continued sensitivity under those conditions. Sound energy requirements are relatively low compared with light production. This makes acoustic communication efficient in energy-limited environments. However, producing strong signals still incurs metabolic cost, so efficiency remains important. Some deep-sea squid produce clicking sounds by manipulating mantle structures. These sounds may serve defensive or communicative roles. Research continues into their exact function. Biological rhythms not tied to sunlight may still influence communication timing. Internal clocks, food availability cycles, or tidal forces can affect when signals are produced. Human exploration vehicles also generate noise. Careful design aims to minimize disturbance, but some behavioral changes in nearby animals have been observed when submersibles approach. Understanding abyssal communication systems improves ecological knowledge. It helps identify species presence without direct visual observation and reveals behavioral patterns otherwise difficult to detect. Silence, then, becomes relative. What humans interpret as quiet may simply be a soundscape operating outside our sensory range or familiarity. And as communication shifts away from vision toward vibration, chemistry, and occasional flashes of light, the physical landscape itself also becomes an important factor. The seafloor is not uniform. It contains mountains, trenches, plains, and geological features that shape how organisms live, move, and interact in these dark waters. When most people picture the bottom of the ocean, they often imagine a flat, sandy surface stretching endlessly in every direction. That mental image is understandable because shallow coastal areas, beaches, and continental shelves can look relatively uniform. But once you move into the true deep ocean, the geography becomes far more varied. There are mountain ranges longer than those on land, trenches deeper than any terrestrial canyon, vast plains, volcanic ridges, hydrothermal fields, and geological formations that shape how life survives there. The seafloor is not a simple surface. It is a complex landscape formed over millions of years by tectonic movement, sediment accumulation, and volcanic activity. One of the most extensive features is the abyssal plain. These regions cover large portions of the ocean floor at depths typically between 3 and 6 kilometers. They are among the flattest areas on Earth. Sediment falling from upper layers settles slowly over time, smoothing irregularities. This sediment often consists of microscopic shells, organic debris, and mineral particles. Although visually calm, abyssal plains are biologically active. Worms, sea cucumbers, crustaceans, and microorganisms inhabit the sediment, processing nutrients delivered from above. Despite their flatness, abyssal plains are not empty. Subtle ridges, burrows, feeding tracks, and occasional rocky outcrops provide microhabitats. Even small variations in terrain can influence water flow and nutrient accumulation. Organisms adapt to these subtle gradients. Moving away from plains, mid-ocean ridges form one of the most prominent geological systems on the planet. These underwater mountain chains mark locations where tectonic plates pull apart, allowing magma to rise and solidify as new crust. The global ridge system extends tens of thousands of kilometers. Its peaks can rise thousands of meters above surrounding seafloor. These ridges influence ocean circulation patterns. Water moving across them creates turbulence and mixing that affect nutrient distribution. Biological communities often cluster along ridge slopes where food availability improves. Volcanic activity along ridges produces hydrothermal vents, which we will discuss in detail later. These vents release mineral-rich fluids, creating localized ecosystems distinct from surrounding deep-sea environments. Seamounts are another significant feature. These underwater mountains form from volcanic activity but do not reach the surface. Some rise several kilometers from the seafloor. Seamounts alter current flow, creating upwelling zones where nutrients concentrate. This can attract diverse marine life even in otherwise food-poor regions. Because seamounts interrupt water flow, they often support richer ecosystems than surrounding plains. Fish, corals, sponges, and invertebrates gather around them. Many species use seamounts as feeding or spawning grounds. Ocean trenches represent the deepest parts of the seafloor. Formed where tectonic plates converge and one slides beneath another, trenches can exceed 11 kilometers in depth. The Mariana Trench is the most well-known example. Conditions there combine extreme pressure, near-freezing temperatures, and complete darkness. Despite these extremes, life exists even in trench environments. Specialized microorganisms, crustaceans, and certain fish species inhabit these depths. Their adaptations reflect pressure tolerance, energy conservation, and efficient feeding on sparse organic material. Submarine canyons carve into continental slopes much like river valleys on land. They channel sediment and organic matter from shallow waters to deeper regions. These transport pathways create nutrient-rich zones, supporting diverse communities. Canyons also influence water movement. Currents funneled through them can accelerate, affecting sediment distribution and biological habitat structure. Some species specialize in canyon environments because of consistent food delivery. Cold seeps provide another unique feature. These areas release hydrocarbons such as methane or hydrogen sulfide from the seafloor. Microbial communities utilize these chemicals as energy sources. Larger organisms, including clams, tube worms, and crustaceans, form symbiotic relationships with these microbes. These chemically driven ecosystems operate independently of sunlight. They demonstrate alternative energy pathways supporting life in deep environments. Sediment composition varies widely across regions. Some areas accumulate fine clay particles. Others contain biogenic sediments composed of microscopic shells. Rocky substrates appear where sediment accumulation is low or currents remove loose material. Habitat structure influences species diversity. Hard surfaces allow attachment for corals, sponges, and anemones. Soft sediments favour burrowing organisms. Each substrate type supports distinct biological communities. Currents interact strongly with seafloor topography. Ridges deflect flow upward. Valleys channel movement. These interactions affect oxygen distribution, temperature gradients, and nutrient transport. Even small geographic features can create localized ecological differences. Temperature in deep-sea environments remains relatively stable, but slight variations occur near geological features. Hydrothermal vents introduce warm fluids locally. Cold seeps may create subtle chemical gradients affecting microbial activity. Mapping the seafloor has historically been challenging. Early explorers relied on weighted lines to measure depth. Modern sonar systems emit sound pulses and measure return times, creating detailed bathymetric maps. Satellite altimetry also contributes by detecting gravitational variations caused by underwater features. Despite technological advances, large portions of the seafloor remain incompletely mapped at high resolution. Some regions have better data than others, but global coverage is still improving. Seafloor geography influences not only biology but also global processes. Ocean circulation patterns affect climate regulation, carbon cycling, and nutrient distribution. Understanding underwater terrain helps model these systems accurately. Subduction zones associated with trenches can produce earthquakes and underwater landslides. These events occasionally generate tsunamis affecting coastal populations. Studying deep-sea geology contributes to hazard assessment. Mineral deposits accumulate in certain deep-sea regions. Polymetallic nodules, cobalt-rich crusts, and sulfide deposits attract industrial interest. Potential mining activities raise ecological concerns because disturbance may impact fragile habitats that recover slowly. Deep-sea coral reefs exist in some locations despite darkness. These corals do not rely on photosynthetic symbionts like shallow water corals. Instead, they capture organic particles from passing currents. Their structures provide habitat for fish and invertebrates. Timescales differ markedly compared with surface environments. Sediment accumulation can take thousands of years. Geological features evolve over millions. Biological communities adapt accordingly. Isolation also shapes evolution. Seamounts and trenches can act like islands, separating populations. Over time, species diverge genetically, increasing biodiversity. The seafloor is not static. Tectonic movement, volcanic eruptions, sediment flows, and biological activity continuously reshape it. However, these changes often occur slowly relative to human timescales. Human exploration vehicles have provided direct visual confirmation of these landscapes. Remotely operated vehicles and crude submersibles capture images revealing cliffs, plateaus, fields of nodules, and unexpected structures. Public perception sometimes equates depth with emptiness. Seeing complex underwater terrain challenges that assumption. The deep ocean contains dynamic physical environments influencing life just as mountains and valleys do on land. Geography also affects communication, migration routes, and feeding patterns. Some species follow ridge systems, others inhabit trench walls or canyon floors. Habitat specificity becomes important in conservation planning. Understanding terrain helps explain species distribution. Certain fish appear only near seamounts. Others specialize in sediment plains. Geological context clarifies ecological patterns. Environmental stability varies by feature. Plains remain relatively consistent. Vent fields may fluctuate as geological activity changes fluid flow. Species adapt to these stability differences. Scientific collaboration across geology, biology, chemistry, and oceanography remains essential. Deep-sea systems integrate multiple disciplines. As attention shifts from terrain itself to specific localized environments, hydrothermal vent systems stand out because they support ecosystems entirely independent of sunlight. These environments illustrate how life can thrive using chemical energy alone, further expanding understanding of what deep ocean life can look like and how it functions. Far below the reach of sunlight, where temperatures remain cold and pressure is immense, there are places on the seafloor where conditions suddenly change. These are hydrothermal vents, openings in the ocean crust where geothermally heated water emerges. They are often described as oases in total darkness because they support dense communities of life in regions that would otherwise have relatively sparse biological activity. The contrast between surrounding seafloor and these localized hotspots can be striking, not visually in terms of brightness, but in terms of biological abundance. Hydrothermal vents form primarily along tectonic plate boundaries, especially mid-ocean ridges where plates pull apart. Magma beneath the crust heats seawater that seeps into cracks. This heated water dissolves minerals from surrounding rock and eventually rises back to the seafloor through vent openings. When it emerges, it can be extremely hot, sometimes exceeding 350 degrees Celsius, although pressure prevents boiling. The vent fluids mix with cold seawater, creating steep temperature gradients within short distances. These vents often produce chimney-like structures known as black smokers or white smokers. Black smokers emit dark plumes rich in metal sulfides that precipitate when hot fluid meets cold seawater. White smokers release lighter-coloured mineral deposits such as barium, calcium or silicon compounds. Over time, mineral accumulation builds towering chimney formations. Before the discovery of hydrothermal vent ecosystems in the late 1970s, scientists assumed that all oceanic life ultimately depended on sunlight. The existence of thriving communities entirely independent of photosynthesis challenged that assumption. Instead of relying on solar energy, these ecosystems depend on chemosynthesis. Chemosynthesis involves microorganisms converting chemical energy from vent fluids into organic matter. Bacteria and archaea use compounds such as hydrogen sulfide, methane, or reduced metals as energy sources. These microbes form the base of the food web around vents, much like phytoplankton do in sunlit waters. Larger organisms often maintain symbiotic relationships with these microbes. Tube worms are a well-known example. Some species lack digestive systems entirely. Instead, they house chemosynthetic bacteria within specialized tissues. The bacteria produce organic compounds that nourish the host. The worm provides access to vent chemicals and oxygen carried in seawater. These tube worms can grow quite large, sometimes exceeding 2 meters in length. Their bright red plumes contain hemoglobin adapted to transport both oxygen and sulfide without toxicity. The vivid colour contrasts with the otherwise dark environment, though it has no visual signalling function in darkness. It reflects biochemical properties rather than display. Vent communities also include clams, mussels, shrimp, crabs, fish, and numerous smaller invertebrates. Many possess unique adaptations for high temperature tolerance, chemical exposure, and pressure stability. Some shrimp species cluster directly near vent openings, enduring conditions that fluctuate rapidly between very hot and very cold water. Temperature variation around vents is extreme compared with typical deep-sea stability. Just centimetres can separate near-freezing seawater from fluid hot enough to damage unadapted tissue. Organisms occupy narrow thermal niches, positioning themselves where conditions remain tolerable. Chemical toxicity presents another challenge. Hydrogen sulfide, abundant in vent emissions, is poisonous to many organisms because it interferes with cellular respiration. Vent species have evolved biochemical mechanisms to tolerate or utilize these compounds. Hemoglobin variants in tube worms, for instance, bind sulfide safely. Pressure remains high even at vent sites, so organisms must handle both chemical extremes and mechanical stress simultaneously. Cellular membranes, enzyme systems, and metabolic pathways reflect these combined constraints. Vent ecosystems can develop quickly after geological activity creates new openings. Microbial colonization begins first, followed by larger organisms. Conversely, vents can become inactive when fluid flow ceases, leading to community decline. This dynamic nature contrasts with the relative stability of surrounding abyssal plains. Larval dispersal between vent sites is an area of ongoing research. Because vents are patchy and sometimes transient, species must spread across large distances to colonize new sites. Ocean currents, larval buoyancy, and chemical cues all play roles. Bioluminescence occurs in some vent organisms, but is generally less dominant than in mid-water zones. Chemical energy availability reduces reliance on light-based hunting or communication strategies. Mineral deposits formed around vents attract industrial interest due to metal concentrations. Potential mining raises ecological concerns because vent communities may recover slowly if disturbed. Research continues into how resilient these ecosystems are. Hydrothermal vent discovery also influenced astrobiology. If life can thrive without sunlight using chemical energy on Earth, similar processes might occur on icy moons with subsurface oceans, such as Europa or Enceladus. Studying vents informs hypotheses about extraterrestrial life possibilities. Scientific exploration of vents relies on remotely operated vehicles, deep-diving submersibles, and specialized sampling equipment. Maintaining sample integrity under pressure remains challenging. Some experiments attempt to replicate vent conditions in laboratories. Microbial diversity around vents is extensive. Many species remain uncharacterized. Their metabolic pathways provide insights into biochemical versatility under extreme conditions. Vent chimneys themselves serve as habitats. Their porous mineral structure offers surfaces for microbial colonization and shelter for small invertebrates. As chimneys grow, they create complex microhabitats. Fluid chemistry varies by location. Different vent fields emit distinct mixtures of metals, gases, and dissolved compounds. This variation influences which species dominate particular sites. Soundscape characteristics around vents differ slightly from surrounding areas due to fluid flow and geological activity. These acoustic signatures may provide orientation cues for some organisms. Light from submersibles reveals striking visual scenes: dense tube worm colonies, swarms of shrimp, mineral chimneys releasing dark plumes. Without artificial light, however, these communities exist in complete darkness. Energy flow through vent ecosystems demonstrates efficiency. Chemosynthetic microbes convert inorganic compounds into biomass, supporting higher trophic levels. This energy pathway operates independently of surface productivity. Vent research has expanded understanding of Earth's biogeochemical cycles. Chemical exchange between crust and ocean influences global nutrient budgets and potentially climate processes over geological time. The transient nature of vents means species often possess dispersal mechanisms allowing rapid colonization. Larvae capable of surviving long periods in the water column increase colonization success. Some organisms exhibit temperature tolerance ranges wider than previously thought possible. Studying these adaptations informs biotechnology, including enzyme applications in industry. Visual impressions of vent communities sometimes appear dramatic because of chimney structures and dense biological clusters. Yet these are localized features within vast dark ocean expanses. Understanding hydrothermal vents underscores the diversity of strategies life employs to obtain energy. Sunlight is not the sole driver. Chemical gradients, pressure, and geological activity all contribute. And beyond vents, similar chemically driven habitats exist, such as cold seeps, where methane and hydrocarbons fuel microbial communities. These environments further illustrate how life persists in darkness, using alternative energy sources, expanding the range of possible biological adaptations in the deep ocean. For most of human history, the connection between life and sunlight seemed obvious. Plants grow toward light. Crops fail without it. Forests depend on it. Even in the ocean's upper layers, microscopic phytoplankton capture sunlight and form the foundation of marine food webs. Remove sunlight, and the assumption was that life would fade away. That belief persisted until deep-sea exploration revealed ecosystems thriving far below the photic zone, entirely independent of solar energy. The key to understanding how that is possible lies in chemosynthesis. Chemosynthesis is a biological process through which certain microorganisms produce organic matter using chemical energy instead of light energy. In photosynthesis, plants and phytoplankton use sunlight to convert carbon dioxide and water into sugars. In chemosynthesis, microbes use chemical compounds such as hydrogen sulfide, methane, ammonia, or reduced metals as energy sources. The outcome is similar. Carbon dioxide is converted into organic molecules that form the base of a food web. The energy source, however, is entirely different. To understand why this matters, it helps to consider the environmental context. In deep ocean environments beyond sunlight's reach, photosynthesis is impossible. Yet chemical gradients exist wherever geological processes introduce reduced compounds into seawater. Hydrothermal vents and cold seeps are prime examples. These areas release chemicals from Earth's crust, creating energy opportunities for specialized microbes. At hydrothermal vents, seawater heated by magma interacts with surrounding rock. This process releases hydrogen sulfide and other reduced compounds into the water. Chemosynthetic bacteria oxidize hydrogen sulfide, meaning they combine it with oxygen to release energy. That energy powers the fixation of carbon dioxide into organic matter. In simple terms, they build biomass from inorganic ingredients using chemical reactions rather than sunlight. Methane seeps function similarly, but rely on methane as an energy source. Methane oxidizing bacteria convert methane into usable energy, again supporting carbon fixation. In both cases, microbial life forms the primary producers of the ecosystem. The biochemical pathways involved are complex but highly efficient under the right conditions. Enzymes specific to these microbes facilitate oxidation reactions. These reactions release electrons, which move through cellular pathways to generate ATP, the molecule cells use to store and transfer energy. With ATP available, carbon dioxide can be incorporated into organic molecules. These chemosynthetic microbes exist as free-living organisms in vent plumes, attached to mineral surfaces, or as symbionts within larger animals. In some cases, larger organisms depend entirely on these microbial partners. Tube worms at hydrothermal vents provide a well-known example. They lack mouths and digestive systems. Instead, they house dense populations of chemosynthetic bacteria in a specialized organ called a trophosome. The bacteria supply nutrients directly to the host. Clams and mussels near vents and seeps also maintain symbiotic bacteria within their gill tissues. These bacteria perform chemosynthesis, and the host animal receives organic compounds in return. This arrangement reduces reliance on scarce drifting food particles. Chemosynthesis is not limited to extreme environments. Some chemosynthetic processes occur in shallow sediments and even within certain terrestrial ecosystems. However, its ecological dominance in deep-sea vent and seep habitats highlights its importance in environments devoid of sunlight. The existence of chemosynthetic ecosystems reshaped scientific understanding of energy flow on Earth. It demonstrated that life does not require sunlight directly. Instead, it requires an energy source capable of driving carbon fixation. Chemical gradients can fulfill that role under appropriate conditions. Temperature at vent sites often fluctuates significantly. Chemosynthetic microbes adapt to wide ranges, from near freezing water adjacent to vent openings to extremely hot fluid closer to emission points. Enzyme systems must remain stable across these gradients. Pressure also influences chemosynthesis. High pressure affects molecular interactions and gas solubility. Microbial species thriving at depth possess pressure-adapted enzymes and membranes, ensuring metabolic processes continue efficiently. Oxygen availability plays a role. Many chemosynthetic reactions require oxygen as an electron acceptor. In some deep-sea zones where oxygen is limited, alternative electron acceptors such as nitrate may be used instead. This flexibility expands potential habitat range. Chemosynthetic productivity can be substantial locally. Vent communities often appear dense compared with surrounding seafloor, because chemical energy input supports high biomass concentration within a small area. However, these ecosystems are patchy. Vent fields are separated by large expanses of low-energy environment. Species adapted to vents must disperse between sites when geological activity creates new habitats. Carbon cycling within chemosynthetic systems differs from photosynthetic ones. Instead of relying on surface-derived organic matter, vents and seeps produce carbon locally. This creates partially independent food webs. Scientists study stable isotope ratios in vent organisms to trace energy sources. Isotopic signatures reveal reliance on chemosynthetically derived carbon rather than photosynthetic input. Some chemosynthetic microbes exist in the deep ocean water column, oxidizing trace amounts of reduced compounds. While less concentrated than at vents, these processes contribute to global biogeochemical cycles. The discovery of chemosynthesis influenced theories about the origin of life. Early Earth likely experienced extensive volcanic and hydrothermal activity. Chemical energy sources may have supported primitive life forms before widespread photosynthesis evolved. Astrobiologists consider chemosynthesis a key possibility for extraterrestrial life. Icy moons with subsurface oceans and geological activity could host chemical gradients similar to Earth's vents. Energy efficiency in chemosynthesis varies depending on chemical substrate. Hydrogen sulfide oxidation yields substantial energy, supporting larger biomass concentrations. Vent and seep ecosystems illustrate cooperation between geology and biology. Geological processes supply chemicals. Biological processes convert them into living matter. Some vent microbes exist in extreme temperature ranges, known as thermophiles. These organisms tolerate heat levels lethal to most life forms. Studying them informs industrial enzyme applications. Chemosynthetic communities often include grazing organisms feeding directly on microbial mats. Others prey on grazers, forming multi-level food webs. Life without sunlight does not mean life without structure. Vent fields can support dense aggregations, forming complex communities with species interactions similar to surface ecosystems. Understanding chemosynthesis expands definitions of habitable environments. It challenges assumptions that light is mandatory for life. In broader ocean context, even regions not directly associated with vents may host microbial chemosynthesis within sediments. Chemical gradients created by organic matter breakdown can fuel localized production. Human impact on chemosynthetic ecosystems remains a concern. Mining or drilling near vent sites could disrupt unique biological communities not found elsewhere. Continued exploration reveals new vent fields and seep systems, each with distinct chemical profiles and species assemblages. These discoveries reinforce a key idea. Deep sea life is not simply surviving in darkness. It is actively thriving by exploiting chemical energy pathways that function independently of the sun. And as chemosynthetic systems illustrate alternative energy foundations, they also highlight how deeply different deep ocean life can be from surface-based expectations. Feeding strategies, body design, growth rates, and behavior continue evolving under constraints of darkness, pressure, and chemical variability, shaping organisms in ways that often seem unfamiliar at first glance. Once you move far enough below the sunlit layers of the ocean, the pace of life begins to change in ways that are not always obvious at first glance. Movements become slower. Growth takes longer. Feeding opportunities appear less predictable. Many deep-sea animals behave differently from their shallow water relatives not because they are less capable, but because the environment rewards a different strategy. Energy efficiency becomes the dominant rule. Aging, movement, and hunting all reflect that shift. Temperature plays a major role in this. Most deep-sea environments remain cold, often just a few degrees above freezing. Cold temperatures slow biochemical reactions. Metabolism decreases. Cells process nutrients more slowly. Growth rates decline. As a result, many deep-sea species mature later than comparable surface organisms. Some fish that would reach adulthood in a few years near the surface may take decades at depth. This slower pace often leads to longer lifespans. Certain deep-sea fish species, such as orange roughy and some rockfish, have been documented living well over a century. Their tissues accumulate age markers slowly because metabolic turnover is reduced. Longevity becomes part of the survival strategy. When food is scarce and environmental conditions remain stable, investing in long-term survival, rather than rapid reproduction, can be advantageous. Food availability is one of the strongest influences on behaviour. In sunlit waters, Primary productivity from phytoplankton supports active food chains. In deep environments, food often arrives as drifting organic material from above, occasional large carcasses, or localized chemical energy sources such as vents. Because meals are unpredictable, animals cannot rely on frequent feeding. This unpredictability encourages opportunistic hunting. Many deep-sea predators possess large mouths, expandable stomachs, and flexible jaws. When prey appears, they take full advantage. Some species can consume animals nearly their own size. Passing up a rare opportunity could mean waiting a long time for another. Movement patterns reflect energy conservation. Fast, continuous swimming requires substantial energy. Where food intake is irregular, conserving energy becomes more important than speed. Many deep-sea animals adopt slow, cruising, hovering, or drifting behaviours. This does not mean they cannot move quickly. Some can produce short bursts of speed when necessary, but routine activity remains economical. Predation strategies shift accordingly. Ambush hunting becomes common. Remaining still reduces energy expenditure and lowers detectability. Sensitive sensory systems allow detection of prey movement without constant searching. Once prey approaches within range, a rapid strike occurs. Sensory reliance changes too. Vision becomes less dominant in darkness. Some species develop highly sensitive eyes for detecting faint bioluminescence. Others rely more on vibration detection, chemical sensing, or electrical cues. These senses guide hunting behavior when visual information is limited. Vertical migration represents another behavioral adaptation. Some species ascend hundreds of meters at night to feed on organisms that move upward from deeper layers. This daily vertical movement, sometimes called diel vertical migration, is one of the largest animal migrations on Earth in terms of biomass. By feeding higher and returning deeper by day, animals balance food access with predator avoidance. Pressure stability influences movement as well. Rapid vertical changes in depth affect internal pressure balance. Deep-sea species adapted to constant pressure may avoid sudden ascents or descents. Gradual movement minimizes physiological stress. Energy storage mechanisms support irregular feeding. Lipid reserves, slow digestion, and efficient nutrient extraction allow animals to survive extended periods without food. Some species can endure months between substantial meals. Reproductive timing reflects these constraints. Instead of frequent spawning, some deep-sea species reproduce less often but invest more resources in each offspring. Larger eggs, protective behaviours, or symbiotic reproductive strategies increase survival probability. Body composition influences aging indirectly. Reduced muscle mass and lower metabolic activity decrease cellular wear over time. Cold temperatures also slow oxidative damage processes, contributing to longevity. Growth patterns differ from surface relatives. Some species grow slowly but continuously throughout life. Others reach maturity late but maintain stable body size afterward. Age determination studies using otoliths, ear stones in fish, reveal surprisingly slow growth increments in deep species. Ecological stability also plays a role. Deep environments experience fewer seasonal fluctuations than surface waters. Stable conditions favour long-lived organisms adapted to consistency rather than rapid change. Hunting tools evolve accordingly. Bioluminescent lures, sensitive lateral lines, and chemical detection systems replace reliance on visual pursuit. The anglerfish's lure, for example, allows prey attraction rather than active chasing. Social behaviour often differs too. Lower population density reduces frequent encounters. Some species are solitary by necessity. Others form loose aggregations near food sources or geological features like seamounts. Another factor involves skeletal structure. Reduced bone density lowers metabolic cost but also limits rapid acceleration. This reinforces slow, deliberate movement patterns. Oxygen availability influences metabolism as well. Cold water holds more dissolved oxygen, which supports basic physiological processes even at low metabolic rates. However, oxygen distribution varies regionally, affecting species distribution. Predator diversity may be lower in some deep zones compared with coastal reefs. Reduced predation pressure allows slower movement strategies to remain viable. Where predators do exist, they often share similar energy conservation adaptations. Scientific observation has improved understanding of these patterns. Long-duration submersible recordings reveal natural behavior without disturbance. Earlier observations sometimes misinterpreted slow movement as inactivity or weakness. Human perception tends to equate activity with vitality. When deep-sea animals move slowly, they can appear lethargic or fragile. In reality, they are operating at an optimal pace for their environment. Comparisons with terrestrial cold environments provide partial analogies. Arctic or Antarctic animals also exhibit slower metabolic rates and energy conservation strategies. However, deep-sea conditions combine cold with darkness and pressure, creating unique challenges. Evolutionary timescales matter here. These adaptations did not appear suddenly. Gradual selection over millions of years refined metabolic efficiency, sensory systems, and behavioral patterns. Deep-sea research continues uncovering variations. Not all species follow the same patterns. Some remain active hunters, others specialize in scavenging. Diversity remains high despite common environmental constraints. Human impacts such as deep-sea fishing can disrupt long-lived species disproportionately. Slow reproduction rates mean population recovery takes longer than in surface ecosystems. Understanding aging patterns informs conservation. Knowing that certain species mature late helps guide sustainable harvesting policies. Movement ecology studies use tagging technology to track deep-sea animals. These studies reveal migration routes, habitat preferences, and behavioral rhythms previously unknown. Chemical energy ecosystems like hydrothermal vents introduce exceptions. Higher localized energy availability supports more active communities compared with surrounding plains. Nevertheless, the overarching theme remains consistent. Darkness, pressure, cold, and limited food shape how deep-sea animals age, move, and hunt. Their strategies prioritize efficiency over speed, longevity over rapid turnover, and sensory specialization over visual dominance. And as humans observe these patterns, another layer emerges. Our own perception of these animals, shaped by surface expectations, influences how alien they appear. Understanding that psychological component helps explain why deep-sea life often feels unfamiliar even when its adaptations follow clear biological logic. When people first see footage from the deepest parts of the ocean, the reaction is often immediate and emotional. Words like alien, unreal, disturbing, or otherworldly appear quickly in comments and conversations. The interesting part is that these creatures are not alien in any literal sense. They evolved here, under Earth's physical laws, shaped by natural selection like every other organism. The sense of alienness does not come from biology alone. It comes from perception. Human perception is shaped by familiarity. From childhood, most people are exposed to a consistent set of animal forms. Mammals with fur, birds with feathers, fish with recognizable proportions, insects with predictable body segments. Even when encountering unusual species, there is often a basic structural template the brain can categorize quickly. 2 eyes in front, a mouth below, symmetry, limbs arranged in expected ways. When those patterns are disrupted, classification becomes slower. The brain relies heavily on pattern recognition. It uses mental shortcuts to identify objects rapidly. This is efficient in daily life. You do not consciously analyze every dog you see to determine whether it is a dog. The shape, movement, and features match stored templates. With deep-sea organisms, many of those templates fail. Transparent bodies reveal internal organs. Eyes may be unusually large or absent. Jaws may extend far beyond typical proportions. Movement may be slow and drifting rather than purposeful and quick. The brain hesitates. There is also the issue of context. Humans evolved in environments filled with light. Shadows, colours, and depth cues help orient perception. Deep-sea footage often shows bright subjects illuminated against black backgrounds. There is no horizon, no reference point, no visible ground. Without context, scale becomes ambiguous. A small shrimp can look enormous. A large organism can seem suspended in empty space. That visual isolation enhances strangeness. Lighting contributes strongly. Artificial lights used by submersibles create stark contrasts. Shadows fall sharply. Features stand out more dramatically than they would in diffuse natural light. Because the surrounding water remains pitch black beyond the light beam, the illuminated animal appears to emerge from nothingness. Another psychological factor involves movement. Humans associate smooth, familiar motion with living organisms. Terrestrial animals walk, run, or fly in ways consistent with gravity and air resistance. Underwater movement obeys different physics. Buoyancy reduces apparent weight. Slow undulations or drifting can look ghost-like because they lack the rhythm the brain expects. Facial recognition bias plays a role as well. Humans are highly attuned to faces. We look for eyes, mouths, and expressions. When we see exaggerated eyes or large toothy mouths, emotional responses trigger quickly. The amygdala, a brain structure involved in threat detection, responds to unusual facial features even if there is no real danger. Colour absence adds another layer. In dim or colourless environments, contrast replaces hue. Many deep-sea animals appear monochromatic. Without colour cues, identification becomes harder. The brain may interpret muted tones as lifeless or artificial. There is also a concept in psychology known as the uncanny valley. It refers to the discomfort people feel when something appears almost but not quite human. While deep-sea animals are not human-like, a similar effect can occur when an organism resembles familiar animals but with altered proportions. The near familiarity combined with deviation creates tension. Cultural influence amplifies these reactions. Films, literature, and art often depict extraterrestrial life as tentacled, glowing, or translucent. When real deep-sea creatures share those features, prior exposure primes interpretation. Instead of viewing them as biological adaptations, viewers map them onto fictional narratives. Fear of the unknown contributes too. Darkness historically signaled potential danger for humans. Environments where visibility is low can increase anxiety. Even when viewing safe footage, subconscious associations may persist. Scale perception also affects reaction. Without clear size references, brains struggle to gauge threat level. An organism that might be only a few centimeters long can appear imposing on a screen. Scientific explanation reduces alien perception over time. As viewers learn about pressure adaptation, energy conservation, and chemosynthesis, features begin to make sense. Knowledge shifts interpretation from emotional to analytical. Exposure plays a significant role. Marine biologists who regularly observe deep-sea organisms rarely describe them as frightening. Familiarity replaces novelty. The brain updates its templates. Media framing influences emotional response. Dramatic music, suspenseful narration, or selective editing can amplify alien impressions. Neutral presentation often results in calmer reactions. There is also a curiosity component. Humans are drawn to novelty. Unfamiliar forms trigger interest as well as unease. That combination fuels fascination with deep-sea exploration. Evolutionary history shapes perception. Humans evolved as land-based primates with limited aquatic experience. Marine life, particularly at depth, exists outside ancestral familiarity. Our brains did not evolve to categorize gelatinous, bioluminescent organisms quickly. Technological mediation further distances perception. Most people experience deep-sea life through screens. Two-dimensional video lacks depth cues and may exaggerate contrast, reinforcing strangeness. Language choices matter. describing creatures as monsters or aliens frames interpretation before analysis begins. Using neutral biological terms shifts tone. Education about ecological function reduces emotional bias. When viewers understand that large jaws reflect food scarcity, not aggression, interpretation changes. There is also aesthetic adaptation. Repeated exposure to unusual forms often leads to appreciation rather than discomfort. What initially appears disturbing can later seem elegant. Children may respond differently than adults. Without entrenched templates, younger viewers sometimes accept unusual forms more readily. Scientific outreach increasingly emphasizes context to counteract exaggerated alien framing. Accurate scale bars, environmental shots, and calm narration help ground perception. The psychology of alien perception highlights a broader principle. Unfamiliar does not mean unnatural, it means outside prior experience. Understanding these psychological processes clarifies why deep-sea organisms often feel so different. The reaction originates as much in the observer as in the organism, and as exploration technology continues improving, allowing clearer, more detailed footage from extreme depths, the interplay between perception and reality becomes even more important. The tools we use to see the deep ocean shape how alien it appears, and understanding those tools provides another step towards separating biological adaptation from psychological interpretation. Seeing the deepest parts of the ocean is not something humans can do directly without assistance. Pressure alone prevents unprotected descent beyond relatively shallow depths, and darkness eliminates natural visibility long before extreme pressure becomes an issue. What we know about the abyss exists largely because of technological tools developed over decades. Cameras, submersibles, sonar systems, robotic vehicles, and specialized sensors have gradually opened access to environments that were once entirely out of reach. Understanding how these tools work helps explain why deep-sea life often appears the way it does in footage. One of the earliest methods for studying ocean depth involved weighted lines lowered from ships. Sailors would drop a rope with a heavy weight attached and measure how much line paid out before reaching the seafloor. This approach provided rough depth estimates but offered no visual information. Still, it established that the ocean was far deeper than initially assumed. The introduction of sonar revolutionized mapping. Sonar works by sending sound pulses downward and measuring how long it takes for echoes to return. Because sound travels efficiently through water, this method allows detailed mapping of underwater terrain. Modern multi-beam sonar systems create high-resolution bathymetric maps showing ridges, trenches, plains, and seamounts. While sonar reveals geography, visual observation requires cameras capable of operating under high pressure and low light. Early underwater cameras were limited by film capacity, lighting constraints, and pressure resistance. Advances in material science and electronics gradually improved performance. Pressure-resistant housings became essential. At depths of several kilometers, external pressure can crush ordinary equipment. Camera housings are built from thick metal alloys or specialized composites designed to maintain structural integrity. Seals must remain watertight under constant stress. Lighting presents another challenge. Natural sunlight disappears quickly underwater. Artificial lights attached to submersibles or remotely operated vehicles provide illumination. These lights must balance brightness with energy efficiency. Too much light can disturb organisms, too little produces unusable footage. Modern deep-sea lighting often uses high-intensity LEDs because they generate strong illumination with relatively low heat output. Heat management is important because enclosed equipment dissipates heat slowly underwater. Crewed submersibles marked a major step forward. Vehicles such as Alvin, Trieste, and more recent deep-diving craft allow scientists to descend in protective pressure-resistant capsules. Thick, spherical hulls distribute external pressure evenly. Windows made from specialized acrylic or quartz allow observation. Operating a crewed submersible involves complex logistics. Support ships coordinate launches and recoveries. Life support systems provide breathable air, temperature control and communication links. Missions often last several hours. Remotely operated vehicles, or ROVs, extend exploration further. These tethered robots are controlled from surface ships via cables carrying power and data. Cameras, robotic arms, sampling tools and sensors can be mounted on ROVs. Because no humans are on board, ROVs can remain at depth longer. Autonomous underwater vehicles, or AUVs, operate without tethers. They follow programmed routes, collecting data and imagery. AUVs are useful for mapping large areas or conducting repetitive surveys. After completing missions, they return to the surface for data retrieval. Camera sensitivity improvements have transformed imaging. Low-light sensors now capture details previously invisible without intense illumination. Some systems use infrared or specialized wavelengths less disruptive to marine life. Acoustic imaging complements visual cameras. Sound-based imaging can reveal objects or animals beyond visible light range. This technique helps locate targets before deploying cameras. Sampling technology allows collection of biological specimens, water samples, and sediment. Pressure-retaining containers help preserve organisms in near-native conditions during ascent, reducing distortion. Communication between deep vehicles and surface teams relies on acoustic signals. Radio waves do not travel well through seawater, so sound-based communication becomes standard. Data rates are slower than terrestrial wireless systems, but sufficient for control and telemetry. Navigation underwater presents difficulties because GPS signals do not penetrate water. Vehicles rely on inertial navigation systems, acoustic beacons, and seafloor mapping references to determine position. Temperature, pressure, and chemical sensors provide environmental context alongside visual observation. Understanding habitat conditions helps interpret biological behavior. Long-duration landers represent another exploration approach. These stationary platforms are placed on the seafloor to record video, sound, and environmental data over extended periods. They reveal natural behavior unaffected by vehicle presence. Satellite technology contributes indirectly. Surface measurements of sea height variations allow inference of large-scale seafloor structures. Combined with sonar data, this improves mapping accuracy. Robotic manipulation tools on ROVs enable specimen collection, equipment placement, and experimental setups. Precision control is essential because visibility and maneuverability are limited. Data storage and transmission improvements allow high-definition video capture. Earlier expeditions relied on short clips due to storage limits. Continuous recording now provides more complete behavioral context. Energy supply remains a constraint. Batteries, power cables, and energy-efficient electronics all factor into mission duration. Advances in battery technology extend operational time. Material science developments improve pressure tolerance. Titanium alloys, syntactic foam for buoyancy, and advanced seal materials enhance reliability. Public outreach increasingly uses live-stream dives. This allows wide audiences to observe exploration in real time, reducing the sense of distance between humans and deep-sea environments. However, camera presence can influence animal behavior. Lights, noise, and vehicle movement sometimes alter natural responses. Researchers account for this when interpreting observations. Image processing techniques correct color distortion caused by water absorption. Restoring approximate true colors helps scientific interpretation, though it can also make footage appear more dramatic. Machine learning tools now assist in identifying species automatically from video. This accelerates data analysis and biodiversity assessment. Mapping hydrothermal vents, cold seeps, and seamount ecosystems relies heavily on combined sonar and camera systems. Integrated datasets provide comprehensive environmental understanding. Underwater drones designed for specific depths continue emerging. Some focus on mid-water zones, others on trench exploration. Specialized designs optimize performance for each environment. Extreme depth exploration requires reinforced hulls capable of withstanding pressures exceeding 1,000 atmospheres. Only a few vehicles can reach the deepest trenches. International collaboration plays a significant role. Deep-sea exploration is expensive, so research institutions often share resources and data. Educational applications benefit from improved imagery. Clear footage helps communicate scientific findings to the public and supports classroom learning. Despite technological progress, much of the deep ocean remains unexplored visually. Mapping resolution varies, and biological surveys cover limited areas relative to total ocean volume. Understanding how we see the deep ocean clarifies why footage sometimes looks stark or unfamiliar. Artificial lighting, camera perspective, and environmental constraints shape perception, and as exploration technology continues advancing, new discoveries regularly reshape understanding of deep-sea life. Some findings challenge prior assumptions, while others confirm long-standing hypotheses about how organisms adapt to darkness, pressure, and isolation far below the surface. As exploration technology improved and scientists began spending more time observing the deep ocean directly, certain discoveries stood out not simply because they were unusual, but because they forced a change in how science understood life on Earth. Some findings overturned long-held assumptions, others expanded biological theory, and a few reshaped entire research fields. These discoveries did not arrive all at once. They accumulated gradually as instruments improved, expeditions expanded, and researchers learned how to interpret environments that had previously been inaccessible. One of the earliest turning points came from depth sounding in the 19th century. Before systematic measurements, many scientists assumed the deep ocean floor would be largely lifeless, covered with fine sediment but lacking complex ecosystems. Early dredging expeditions began recovering organisms from greater depth than expected, including starfish, worms, crustaceans, and mollusks. These samples demonstrated that life persisted well beyond shallow coastal zones. Although primitive by modern standards, those expeditions established the first reliable evidence that the deep sea was biologically active. The HMS Challenger expedition between 1872 and 1876 marked a major milestone. This global voyage conducted systematic deep-sea sampling, mapping, and biological collection. Thousands of new species were documented. Temperature profiles, seafloor sediments, and chemical data were recorded in ways not previously attempted. The Challenger expedition effectively launched modern oceanography as a scientific discipline. It showed that the deep ocean was not an empty void, but a complex environment deserving sustained study. Another transformative discovery involved the existence of mid-ocean ridges. Sonar mapping during the 20th century revealed long underwater mountain chains running through the world's oceans. These findings contributed to plate tectonics theory, demonstrating that ocean crust forms at spreading centers and moves outward. This geological insight had implications beyond oceanography, influencing understanding of earthquakes, volcanic activity, and continental drift. The descent of the bathyscaphe Trieste into the Mariana Trench in 1960 provided both engineering and biological revelations. The crude submersible reached nearly 11 kilometers below the surface. Observation suggested that even at those extreme depths, where pressure exceeds 1,000 atmospheres, life persisted. Later expeditions confirmed microbial and animal presence in trench environments. This finding reinforced the resilience of life under extreme conditions. Perhaps the most scientifically disruptive discovery came in 1977, with the identification of hydrothermal vent ecosystems along the Galapagos Rift. Until then, the prevailing assumption was that all ecosystems ultimately depended on sunlight through photosynthesis. Vent communities proved otherwise. Dense populations of tube worms, clams, shrimp and fish thrived around chemical emissions from the seafloor. Chemosynthetic bacteria formed the base of these food webs. This discovery expanded biological theory by showing that life could be sustained entirely by chemical energy rather than solar input. Hydrothermal vent research also contributed to origin of life studies. Some scientists propose that early life on Earth may have originated near similar hydrothermal systems, where chemical gradients provided energy before photosynthesis evolved. This idea remains under investigation but continues influencing astrobiology research. The identification of cold seep ecosystems provided another important example of chemosynthesis. Unlike vents driven by heat, cold seeps release hydrocarbons such as methane at relatively low temperatures. Microbial communities oxidize these compounds, supporting diverse biological assemblages. These findings reinforce the idea that chemical energy pathways can sustain ecosystems in multiple deep-sea contexts. Bioluminescence research advanced significantly with improved imaging technology. Scientists discovered that a majority of mid-water deep-sea organisms possess some capacity for light production. This realization shifted understanding of communication, camouflage, and predation strategies in dark environments. The ecological role of light changed from occasional curiosity to central organizing principle in certain habitats. The discovery of giant squid in natural deep-sea environments represented another milestone. For centuries, these animals were known primarily from stranded specimens or fragments. Capturing live images confirmed their habitat preferences, behavior, and morphology. It demonstrated that even large elusive species remained largely undocumented until technology allowed direct observation. Similarly, the identification of colossal squid and other large deep-sea cephalopods expanded knowledge of predator-prey relationships in abyssal zones. These species showed that large body size remains viable even in energy-limited environments, when supported by appropriate adaptations. Deep-sea coral reefs presented another surprise. Unlike shallow tropical reefs dependent on photosynthetic symbionts, deep corals rely on particulate feeding. Their existence expanded understanding of reef ecology and highlighted the importance of non-photosynthetic coral systems. These habitats support fish populations and biodiversity previously unrecognized. Long-term seafloor observatories produced insights into deep ocean stability and variability. Instruments left on the seabed for months or years recorded currents, temperature changes, sediment movement, and biological activity. These observations showed that deep environments, while relatively stable compared with surface waters, still experience episodic disturbances such as sediment flows, chemical fluctuations, and biological migrations. The discovery of extensive deep scattering layers through sonar surveys provided another important insight. These layers, composed of small fish, squid, and zooplankton, migrate vertically daily. During daylight they remain deep, ascending at night to feed. This diel vertical migration represents one of the largest biomass movements on the planet. Its scale influenced global carbon cycling models. Microbial discoveries also reshaped scientific understanding. Deep subseafloor microbial communities exist within sediments and crustal rocks far below the seafloor. These organisms survive on minimal energy, sometimes dividing only once in years or decades. Their existence expanded the known limits of life and influenced estimates of global biomass. Research into extremophiles, organisms thriving under extreme pressure, temperature, or chemical conditions, provided applications beyond marine science. Enzymes from these organisms found uses in biotechnology, medicine, and industrial processes. Another important discovery involved methane hydrate deposits. These ice-like structures trap methane within seafloor sediments. Their stability affects climate models because methane is a potent greenhouse gas. Understanding hydrate dynamics remains an active research area. Advances in genetic sequencing allowed identification of deep-sea species without direct observation. Environmental DNA sampling detects genetic material in water samples, revealing species presence. This method expanded biodiversity assessment capabilities significantly. Acoustic monitoring of deep oceans led to unexpected findings about marine mammal migration and communication. Long-distance whale calls recorded at depth showed complex acoustic behavior across ocean basins. Exploration of submarine canyons revealed their importance as nutrient conduits from continental shelves to deep basins. This influenced models of sediment transport and carbon sequestration. Discovery of previously unknown fish species in Hadal trenches demonstrated that vertebrate life extends deeper than once thought. Snailfish species adapted to extreme pressure provided insight into vertebrate physiological limits. Deep-sea mining interest prompted ecological baseline studies. These investigations revealed biodiversity levels higher than expected in some sediment plains, informing environmental policy discussions. Underwater volcanic eruptions documented by submersibles provided real-time observation of geological processes shaping ocean crust. Biological colonization following eruptions offered insight into ecological succession in extreme environments. Subsurface ocean crust fluid circulation studies showed chemical exchange between rock and seawater on global scales. This influences nutrient cycles and microbial habitats. The identification of long-lived deep-sea fish species influence fisheries management. Slow growth rates and late maturity make these populations vulnerable to overharvesting. Research into deep-sea plastics and pollution reveal that human impact extends far beyond coastal areas. Microplastics and chemical contaminants appear even in remote deep basins. The cumulative effect of these discoveries has been a gradual but profound shift in how scientists view the deep ocean. Rather than a remote, static environment, it is now understood as dynamic, biologically diverse, and closely connected to global systems. Each discovery also changes public perception. What once seemed unreachable becomes observable. What seemed alien becomes understandable through biological context. And as exploration continues revealing unexpected species, chemical processes and geological features, the deep ocean increasingly appears not as an exception to Earth's biosphere, but as one of its largest and most influential components, shaping planetary processes in ways still being uncovered. When you look at deep-sea creatures and think about how different they appear from surface animals, it can be tempting to imagine that they were somehow designed for strangeness. But there is no sudden creative leap involved. The same process that shaped birds, mammals, reef fish and insects also shaped the organisms living thousands of meters below the surface. The difference lies in isolation, time and environmental constraint. Evolution in the deep ocean operates under conditions that are both extreme and remarkably stable, and that combination produces forms that often look unfamiliar to surface observers. Isolation plays a central role. The deep ocean is not a single uniform space. It is divided by ridges, trenches, seamounts, plains, and chemical habitats like vents and seeps. These features can separate populations physically and chemically. Over long periods, separated populations accumulate genetic differences. Without regular interbreeding, natural selection acts independently on each group. Gradually, distinct species emerge. Seamounts provide a clear example. Rising thousands of meters from the seafloor, they act almost like underwater islands. Species living on one seamount may rarely encounter those from another, even if separated by only tens of kilometers. Currents, depth preferences, and larval dispersal patterns all influence connectivity. Limited exchange encourages divergence. Trenches create another form of isolation. Their extreme depth and steep walls can restrict movement between adjacent basins. Species adapted to trench pressure may not survive at shallower depths, and vice versa. Over time, unique trench-adapted lineages evolve. Hydrothermal vents represent a special case of patchy habitat. Vent fields are scattered along mid-ocean ridges, separated by vast stretches of low-energy seafloor. Species living at vents must disperse between sites via larval stages carried by currents. Because vents can become inactive over geological time, populations may face repeated cycles of colonization and extinction. This dynamic promotes rapid adaptation within a constrained environment. Extreme environmental conditions amplify evolutionary pressure. Cold temperatures, high pressure, darkness, and limited food narrow the range of viable traits. Only individuals with suitable physiological and behavioral adaptations survive to reproduce. Over many generations, traits that might be neutral or even disadvantageous in surface waters become beneficial at depth. Stability contributes as well. Unlike surface environments that experience seasonal temperature shifts, storms, and light fluctuations, many deep-sea habitats remain relatively constant over long timescales. This stability allows specialization. Once a trait proves effective, there may be little environmental pressure to change it. Some deep-sea lineages appear morphologically conservative for millions of years. Energy limitation shapes evolutionary pathways strongly. Traits requiring high metabolic cost are less likely to persist unless they offer significant survival benefit. This encourages reduction of unnecessary structures, slower growth rates, and efficiency in reproduction and feeding. Genetic studies reveal that some deep-sea species have close relatives in shallow waters. These lineages likely originated in surface habitats and gradually colonized deeper zones. Over evolutionary time, genetic mutations accumulated that enhanced pressure tolerance, modified sensory systems, and altered metabolism. Pressure adaptation involves changes at molecular levels. Proteins must maintain structure under compression. Membranes require specific lipid compositions to remain functional. Genes regulating these features show signatures of selection in deep-sea species. Sensory evolution demonstrates divergence clearly. In darkness, genes related to color vision may accumulate mutations, while genes enhancing low-light sensitivity or mechanoreception are preserved. In some species, visual genes become non-functional entirely. Reproductive strategies also evolve under isolation. In sparse populations, finding mates can be challenging. Adaptations such as chemical signaling, hermaphroditism, or parasitic mating arrangements increase reproductive success. Deep-sea gigantism and miniaturization both illustrate evolutionary flexibility. Where conditions favor larger size due to oxygen availability and longevity, size increases. Where energy conservation is paramount, smaller size may be selected. Speciation rates in deep environments remain an area of active research. Some evidence suggests slower rates due to stability and low population density. Other evidence indicates rapid divergence around specialized habitats like vents. Fossil records provide limited insight into deep-sea evolution, because preservation at depth is less common. However, molecular clock analysis helps estimate divergence times. Isolation does not imply complete separation. Currents occasionally transport larvae across distances, maintaining some gene flow. The balance between isolation and connectivity determines evolutionary trajectory. Climate shifts over geological time also influence deep-sea evolution. Changes in ocean circulation, temperature gradients, and oxygen levels alter habitat suitability. Species must adapt or migrate. Mass extinction events have affected deep-sea life differently than surface ecosystems. Some evidence suggests certain deep-sea communities experience less dramatic extinction rates during global events due to environmental buffering. Evolutionary history also explains why some deep-sea species appear related to ancient lineages. Certain groups that declined in shallow waters may persist at depth, where competition differs. Comparative genomics reveals unique gene families in deep-sea organisms associated with stress response, protein folding, and membrane stability. These genetic signatures reflect long-term adaptation. Isolation contributes to endemism. Many deep-sea species are found only in specific regions. This increases biodiversity but also vulnerability to localized disturbance. Biogeographic patterns in the deep ocean differ from terrestrial ones. Barriers are less visible but still significant. Temperature gradients, chemical zones, and depth layers create ecological boundaries. Human perception of evolutionary oddity arises partly because we compare deep-sea species to surface relatives. Without understanding shared ancestry, differences seem exaggerated. Evolution in extreme isolation demonstrates that natural selection operates wherever variation and environmental pressure exist. The deep ocean is not separate from evolutionary processes, it simply applies different constraints. As research continues, genetic sampling expands knowledge of how lineages spread across ocean basins. Some species exhibit surprising connectivity despite depth barriers. The interplay between isolation and dispersal remains central. Too much isolation reduces genetic diversity. Too much connectivity limits divergence. Deep-sea ecosystems display examples of both extremes. Conservation considerations increasingly incorporate evolutionary uniqueness. Protecting isolated populations preserves genetic diversity accumulated over millions of years. Understanding evolution in extreme isolation clarifies that deep-sea life is not alien in origin. It is the outcome of the same gradual processes shaping all biodiversity, guided by environmental context. And as evolutionary pathways continue unfolding in these remote habitats, human imagination often fills gaps with myth and speculation. Long before scientific exploration reached these depths, stories and legends attempted to explain what might dwell in the dark below, shaping cultural expectations long before cameras ever captured real images. Long before submersibles, sonar and underwater cameras made it possible to see the deep ocean directly, people tried to imagine what might exist beneath the surface. The sea has always inspired curiosity but also caution. It was vast, unpredictable, and often dangerous. Storms could destroy ships, coastlines could shift, and sailors occasionally reported unusual sightings. Without reliable ways to verify those reports, imagination filled the gaps. Over centuries, myths and monster stories developed not only from fear, but from attempts to explain an environment humans could not observe directly. Ancient maritime cultures left some of the earliest written descriptions of sea creatures that today would likely be interpreted differently. Greek texts mention large serpents and fish-like beings inhabiting deep waters. Norse sagas describe the kraken, an enormous creature said to drag ships beneath the waves. These stories probably drew on sightings of giant squid, whales, or unusual surface disturbances, combined with storytelling traditions that emphasize drama. Maps from the medieval and early modern periods often included illustrations of sea monsters in unexplored regions. These images were not intended purely as decoration. They reflected uncertainty about what lay beyond known coastlines. Cartographers used them partly as warnings and partly as placeholders for unknown information. Where data was lacking, symbols of danger appeared. Cultural storytelling amplified these images. Sailors returning from long voyages often recounted encounters with unfamiliar animals. Lighting conditions at sea, fatigue, and limited visibility could distort perception. A whale surfacing unexpectedly, or a squid tentacle breaking the surface might easily be interpreted as something more dramatic, especially when retold multiple times. Scientific knowledge during those periods was limited. Without biological classification systems or photographic documentation, distinguishing between species accurately was difficult. Many animals now well understood, such as oarfish or giant squid, were once considered mythical because they were rarely seen intact. Literature reinforced the idea of mysterious depths. Stories about lost cities beneath the sea, hidden kingdoms, or monstrous guardians of the abyss appeared across cultures. These narratives reflected both fascination and caution. The ocean represented opportunity through fishing and trade, but also risk. The age of exploration brought increased contact with unfamiliar marine life. Expeditions encountered species not previously documented in European or Asian records. Reports often mixed observation with speculation. Some descriptions were accurate but incomplete. Others incorporated exaggeration, sometimes unintentionally. As scientific methodology improved in the 18th and 19th centuries, classification systems began organizing marine biodiversity more systematically. Specimens collected during expeditions allowed direct study rather than reliance on anecdote. Still, deep-sea sampling remained difficult, so mystery persisted. The transition from myth to scientific understanding accelerated with technological advancement. Improved diving equipment, dredging tools, and eventually submersibles provided direct observation. Creatures once thought legendary, such as giant squid, were documented through specimens and later video footage. Despite increasing knowledge, cultural imagery did not disappear. 20th century literature and film often portrayed deep-sea environments as settings for suspense or science fiction. Glowing organisms, unusual body forms, and unfamiliar movement patterns lent themselves to dramatic storytelling. These portrayals influenced public perception. Even today, documentaries sometimes frame deep-sea species using language borrowed from fiction. Terms like alien, monster, or mysterious appear frequently, even in otherwise scientific contexts. Psychological factors contribute to this persistence. Humans tend to fill unknown spaces with narrative. The deep ocean, being largely inaccessible historically, served as a natural canvas for imagination. That tendency continues even as knowledge expands. Modern discoveries occasionally revive older myths in updated form. When footage of a rarely seen species emerges, comparisons with legendary creatures often follow. While usually light-hearted, these comparisons demonstrate how cultural memory shapes interpretation. Scientific communication increasingly aims to balance fascination with accuracy. Researchers emphasize ecological function, evolutionary history, and environmental context to counter exaggerated portrayals. Educational outreach highlights that unusual appearance does not imply danger or aggression. Understanding myth development also offers insight into human cognition. People seek explanations for unfamiliar phenomena. Before systematic science, storytelling fulfilled that role. Myths preserved collective attempts to interpret natural events. Some myths contained kernels of truth. Reports of enormous tentacled creatures correspond with known squid species. Accounts of glowing seas reflect bioluminescent plankton blooms. Strange sounds described by sailors may have originated from marine mammals or geological activity. Historical ocean exploration sometimes relied on myth-informed caution. Areas reputed to contain dangers were approached carefully, sometimes leading to more thorough observation. Cultural diversity produced varied ocean myths. Polynesian traditions included ocean guardians reflecting respect for marine resources. Mediterranean cultures described sea deities symbolizing environmental forces. Northern European stories often emphasized perilous waters and large creatures. Artistic representation of sea monsters influenced visual expectations. Paintings, engravings, and later film depictions shaped how people imagined unseen environments. Even scientific illustrators occasionally blended observation with artistic convention. As deep-sea research expanded in the late 20th century, direct imagery began replacing speculation. Submersible footage showed real animals in their natural habitat. This visual evidence gradually reduced reliance on myth. However, unfamiliar appearance still triggers imaginative interpretation. Transparent bodies, glowing organs, or unusual proportions can resemble fictional creatures. The difference now is that scientific explanation accompanies imagery more consistently. Educational programs highlight the transition from myth to evidence-based understanding. Showing historical illustrations alongside modern footage helps illustrate how knowledge evolves. Media literacy also plays a role. Recognizing narrative framing helps viewers distinguish between entertainment and scientific reporting. Public fascination with the deep ocean remains strong, partly because mystery persists. Large areas remain unexplored. New species continue to be discovered. This ongoing process keeps imagination engaged. Scientific institutions often use that fascination constructively, encouraging interest in marine conservation and research funding. Myths about the deep sea are not inherently problematic. They reflect curiosity. Problems arise only when myth replaces evidence in decision-making or education. Modern storytelling sometimes integrates scientific accuracy more deliberately. Documentaries emphasize ecological relationships rather than danger narratives. Research vessels occasionally name newly discovered species after mythological figures, acknowledging cultural heritage while maintaining scientific rigor. Understanding how humans imagine the deep ocean historically provides perspective on current perceptions. What once seemed unknowable now becomes observable through technology, and as technological exploration continues expanding access to remote marine environments, the boundary between imagination and observation keeps shifting. What today appears mysterious may tomorrow become routine scientific knowledge, gradually reshaping how people think about the deep ocean and its inhabitants. When scientists began exploring the deepest parts of the ocean in detail, the goal was usually to understand Earth itself. But as discoveries accumulated, another connection started becoming clear. Conditions in the deep ocean, darkness, extreme pressure, limited energy input, chemical-driven ecosystems, resemble environments that may exist beyond our planet. Studying these underwater habitats has become an important way to think about where life might exist elsewhere, and how it might survive without conditions humans typically associate with habitability. One of the most significant lessons involves energy sources. For a long time, sunlight was assumed to be essential for complex ecosystems. Photosynthesis dominates surface biology, so it seemed logical to treat solar energy as a requirement for life. The discovery of hydrothermal vent communities supported entirely by chemosynthesis challenged that assumption. If microorganisms can build food webs using chemical energy from geological processes, then environments without sunlight may still support life. This realization has influenced research into icy moons in our solar system. Europa, a moon of Jupiter, is believed to contain a subsurface ocean beneath an ice crust. Evidence suggests geological activity may occur there, potentially creating chemical gradients similar to hydrothermal vents. Enceladus, a moon of Saturn, shows signs of water plumes and internal heating. Chemical energy in those environments could theoretically support microbial ecosystems. Pressure tolerance provides another important lesson. Deep-sea organisms routinely experience pressures that would be lethal to humans. Cellular membranes, proteins, and metabolic pathways adapt to maintain function under compression. This suggests that high pressure alone does not preclude life. Subsurface oceans on other worlds may experience similar pressures, yet still remain biologically viable. Temperature extremes also offer insight. While much of the deep ocean remains cold, hydrothermal vent fluids can be extremely hot. Some microorganisms, called thermophiles, thrive at temperatures exceeding those tolerated by most known life. This demonstrates biochemical flexibility. If chemical energy exists, temperature ranges broader than previously assumed might still support life. Darkness, once considered limiting, becomes less critical when alternative energy sources exist. Deep ocean ecosystems operate without sunlight continuously. This informs planetary science because many extraterrestrial environments receive little or no solar illumination. Subsurface habitats, underground aquifers, or ice-covered oceans could still host life if chemical energy gradients are present. Isolation is another parallel. Deep-sea ecosystems often remain separated from surface environments by physical barriers, yet life adapts to these isolated niches successfully. Similarly, extraterrestrial habitats might exist in isolation from planetary surfaces. Studying how Earth organisms handle limited gene flow, sparse populations, and environmental stability helps scientists model potential evolutionary pathways elsewhere. Chemical diversity in the deep ocean broadens understanding of possible metabolic strategies. Microorganisms there use sulfur compounds, methane, iron, and other chemicals as energy sources. These metabolic pathways suggest life does not require oxygen or carbon sources in the same forms humans depend on. Alternative chemistries could sustain organisms under different planetary conditions. Subsurface microbial communities beneath the seafloor offer another analogy. These organisms live within sediments or rock layers with minimal energy input. Some divide only rarely yet remain viable for long periods. This slow metabolic mode may resemble potential extraterrestrial microbial survival strategies in energy-limited environments. Exploration methods developed for deep-sea research also inform planetary exploration technology. Remotely operated vehicles, autonomous sensors, pressure-resistant materials, and chemical detection instruments designed for ocean depths provide engineering models for missions to icy moons or subsurface environments on Mars. Contamination prevention procedures used in deep-sea sampling parallel planetary protection protocols. Scientists aim to avoid introducing surface microbes into pristine environments, both on Earth and during space missions. Maintaining sample integrity is critical for accurate interpretation. Acoustic mapping techniques developed for oceanography inspire approaches for probing subsurface planetary structures. Sound-based imaging may help detect liquid water beneath ice layers on other worlds. The discovery of extremophiles, organisms thriving in conditions once considered uninhabitable, expanded the definition of habitability. Acidic vents, high-pressure sediments, and chemically reactive environments all support life on Earth. This widens the range of environments considered potentially habitable elsewhere. Understanding resilience also informs expectations. Deep-sea ecosystems often recover slowly from disturbance due to low energy input and long lifespans. If extraterrestrial ecosystems exist, they might exhibit similar sensitivity to environmental change. Bioluminescence offers speculative parallels as well. While not necessary for extraterrestrial life, the existence of organisms producing light chemically demonstrates that sensory communication need not rely on sunlight. Alternative signalling mechanisms could evolve in dark environments. Evolutionary timescales provide another perspective. Deep-sea species often evolve slowly due to stable conditions. Extraterrestrial ecosystems, if present, might show similar gradual evolutionary patterns rather than rapid diversification. Carbon cycling in deep oceans highlights non-photosynthetic carbon fixation pathways. This informs climate modelling for Earth and potential atmospheric interpretations for other planets. Interdisciplinary collaboration between oceanographers, microbiologists, geologists, and planetary scientists has grown partly because of these parallels. Insights from one field inform hypotheses in another. Public interest in extraterrestrial life often increases when deep-sea discoveries are publicised. The visual similarity between some deep-sea organisms and fictional alien depictions reinforces curiosity, even if the biological basis remains entirely terrestrial. Scientific caution remains important. Similar environmental conditions do not guarantee similar biological outcomes. Deep ocean analogies guide hypotheses but do not confirm extraterrestrial life. Future missions may involve probes designed to penetrate icy crusts or sample subsurface oceans. Technologies tested in deep-sea conditions provide valuable prototypes for such efforts. Deep ocean research also reminds scientists that Earth still holds many unexplored environments. Discoveries here may precede or parallel discoveries elsewhere. Educational programs increasingly highlight these connections, showing how Earth environments expand our understanding of possible life elsewhere, helps contextualize both oceanography and planetary science. Ethical considerations arise as well. Protecting deep-sea ecosystems while using them as research analogues requires careful balance. Preservation ensures continued scientific study without ecological damage. The broader lesson is that life adapts to available energy sources, not necessarily sunlight. Chemical gradients, pressure stability, and environmental consistency can sustain ecosystems. As exploration continues, both in the oceans and in space, comparisons between these environments will likely deepen. Observations in one domain often suggest new questions in the other. and while the deep ocean offers valuable analogues for extraterrestrial habitats, it also remains a frontier in its own right. Large portions of Earth's seafloor remain poorly explored, meaning that new discoveries there may continue informing not only ocean science, but our broader understanding of where life can exist. For a long time, the phrase last frontier was usually applied to space. Rockets, satellites, planetary missions and telescopes captured public imagination. Yet when scientists look at how much of Earth itself remains directly explored, the deep ocean stands out. A large portion of the planet's surface lies underwater, and most of that water is deep. Despite decades of research, detailed visual exploration covers only a small fraction of the seafloor. The idea of the deep sea as Earth's last frontier reflects not exaggeration but simple geography. One reason exploration remains limited is cost. Deep-sea missions require specialized ships, highly trained crews, sophisticated equipment, and extensive logistical planning. Pressure-resistant vehicles, robotic arms, advanced sensors, and communication systems all add complexity. Compared with land-based research, every hour at depth represents significant investment. Technical challenges extend beyond cost. Pressure, darkness, and cold create harsh operating conditions. Equipment failure can occur easily if seals fail, electronics malfunction, or navigation systems lose accuracy. Redundancy and careful engineering reduce risk but increase complexity. Communication presents another obstacle. Radio waves used for terrestrial communication do not travel well through seawater. Acoustic signals replace them, but bandwidth is limited. Real-time high-resolution data transmission remains challenging, especially at extreme depths. Navigation underwater also differs from surface or aerial environments. GPS signals do not penetrate water effectively. Vehicles rely on acoustic positioning, inertial navigation, and seafloor mapping references. Precision improves with technology, but uncertainty remains higher than on land. Despite these difficulties, exploration continues expanding. Mapping projects aim to produce high-resolution bathymetric maps of the entire seafloor. International collaborations combine sonar surveys, satellite data, and autonomous vehicle missions to improve coverage. Biological exploration remains particularly incomplete. Many deep-sea species are known only from single observations or limited specimens. Some habitats have never been visited directly. Each expedition tends to discover new organisms, suggesting biodiversity remains underdocumented. Chemical and geological exploration also continues. Hydrothermal vent fields, cold seeps, methane hydrate deposits, and mineral-rich nodules attract scientific interest. These features influence global biogeochemical cycles, climate regulation, and potential resource management. Interest in deep-sea mining has increased in recent years. Polymetallic nodules, cobalt-rich crusts, and sulfide deposits contain economically valuable metals. However, ecological concerns accompany industrial interest. Deep-sea ecosystems often recover slowly from disturbance due to low energy availability and long organism lifespans. Environmental monitoring programs aim to understand baseline conditions before any large-scale industrial activity occurs, establishing biodiversity inventories, sediment composition data, and current patterns helps assess potential impact. Climate research increasingly considers deep ocean processes. Heat absorption by oceans influences global temperature regulation. Carbon sequestration in deep sediments affects atmospheric carbon dioxide levels. Understanding these processes requires continued observation. Pollution studies reveal that human impact reaches even remote deep basins. Microplastics, chemical contaminants, and noise pollution appear far from coastal sources. These findings highlight global connectivity of ocean systems. Technological innovation continues improving exploration capability. Smaller autonomous vehicles reduce operational cost. Enhanced battery technology extends mission duration. Improved sensors increase data quality. Artificial intelligence assists in analyzing large data sets. Automated species identification from video footage accelerates biodiversity assessment. Machine learning also helps interpret sonar mapping and environmental sensor data. Public engagement has grown through live-stream deep sea dives. These broadcasts allow viewers to observe exploration in real time, reducing psychological distance between people and remote environments. Educational outreach emphasizes the deep ocean's importance to planetary health. Ocean circulation, climate regulation, nutrient cycling, and biodiversity all connect to deep-sea processes. Policy discussions increasingly include deep-sea conservation. Marine protected areas extend beyond coastal zones to include seamounts, trenches, and vent fields. Protecting unique habitats supports biodiversity preservation. International governance remains complex. Much of the deep ocean lies beyond national jurisdictions. Organisations such as the International Seabed Authority oversee certain activities, but coordination across nations continues evolving. Scientific collaboration plays a major role. Expeditions often include multinational teams sharing expertise, equipment, and data. This approach maximizes efficiency given the scale of the environment. Historical comparison illustrates progress. Early ocean exploration relied on simple-sounding lines. Modern missions deploy robotic fleets, high-definition cameras, chemical analyzers, and genomic sequencing tools. Yet the percentage of the deep ocean directly observed remains relatively small. Estimates vary, but detailed visual coverage represents a fraction of total seafloor area. This leaves significant opportunity for future discovery. Exploration priorities include biodiversity assessment, geological mapping, climate monitoring, and resource evaluation. Balancing scientific curiosity with environmental stewardship remains a central consideration. Cultural perception of the deep sea has shifted gradually. Once viewed primarily as dangerous or mysterious, it is increasingly recognized as ecologically significant and scientifically valuable. Media portrayal influences public interest. Documentaries, educational programming, and scientific outreach help build awareness. Accurate representation supports informed decision-making. Technological crossovers benefit other fields. Materials developed for deep-sea pressure resistance find use in aerospace and engineering. Sensor technologies developed underwater inform environmental monitoring elsewhere. Deep-sea exploration also inspires philosophical reflection. Recognizing how much of our own planet remains unexplored encourages humility about scientific knowledge. Future missions may include permanent deep-sea observatories, expanded autonomous vehicle networks, and integrated global mapping initiatives. Continuous monitoring could reveal long-term environmental trends. Citizen science initiatives occasionally contribute through data analysis or educational engagement. While direct participation at depth is impractical, public involvement in interpretation and outreach continues growing. Economic considerations remain significant. Funding for large-scale oceanographic research competes with other scientific priorities. Demonstrating societal relevance helps sustain support. Ethical considerations involve balancing resource use with conservation. Understanding ecosystem resilience informs responsible policy development. Scientific training programs increasingly include deep-sea specialization. Expertise in robotics, marine biology, geology, chemistry, and data science converges in oceanographic research. As exploration continues, discoveries will likely reshape understanding of Earth systems further. Unknown species, geological features, and chemical processes remain to be documented. The idea of the deep sea as Earth's last frontier therefore reflects ongoing discovery rather than a final destination. Exploration expands incrementally, each mission building on previous knowledge, and as understanding grows, so does appreciation for the complexity of deep ocean ecosystems. Recognizing their importance encourages continued research, conservation efforts, and public engagement with a part of the planet that, despite covering most of it, remains less familiar than many landscapes on land. By the time you've followed this journey from the sunlit surface down into the deepest parts of the ocean, the idea that these places look alien probably feels a little different than it did at the beginning. Not because the creatures or environments have become less unusual, but because the reasons behind that unfamiliar appearance start to make practical sense. Darkness, pressure, cold, isolation, and limited food are not dramatic storytelling elements. They are environmental constraints. Life adapts to constraints, and when the constraints differ strongly from what humans experience daily, the results can look surprising. The deep ocean is not trying to be mysterious. It simply operates under physical conditions that humans rarely encounter directly. Without sunlight, vision loses priority. Without abundant food, energy conservation becomes critical. Under immense pressure, body composition changes. Over millions of years, these pressures shape organisms into forms optimized for survival there, not for visual familiarity to surface observers. One useful way to think about this is to reverse perspective. Imagine a deep-sea organism observing life on land for the first time. Bright colours, rapid movement, large eyes adapted for daylight, reliance on air breathing, dramatic temperature fluctuations, seasonal cycles. From that viewpoint, terrestrial life might appear equally unusual. Familiarity influences interpretation. There is also something steady about deep environments that contrasts with surface variability. Weather, day-night cycles, seasonal changes, and temperature swings dominate surface ecosystems. Deep waters remain comparatively stable. That stability shapes slower life cycles, longer lifespans, and energy-efficient behaviour. It is not inactivity. It is optimization. Scientific exploration continues refining understanding. Every new expedition adds details about biodiversity, geology, chemistry, and ecological interactions. What once seemed unknowable becomes measurable. What once seemed speculative becomes documented. The pattern repeats across scientific history, and the deep ocean is a clear example of that process still underway. Technology plays an important role here. Cameras, sonar mapping, remotely operated vehicles, genetic analysis, and chemical sensors all extend human perception into environments otherwise inaccessible. As tools improve, imagery becomes clearer, data becomes more precise, and interpretations become more accurate. That gradual improvement reduces reliance on imagination alone. At the same time, some degree of mystery remains inevitable. The ocean is vast. Even with modern technology, exploring every region thoroughly takes time. New species continue to be discovered. Geological processes continue reshaping seafloor landscapes. Chemical interactions continue influencing ecosystems in ways still being studied. Human impact reaches even these remote environments. Climate change influences ocean temperature and circulation. Pollution travels through currents. Resource extraction proposals raise questions about ecological resilience. Understanding deep-sea systems helps inform responsible decisions about how to interact with them. There is also a broader perspective to consider. The deep ocean connects to global processes more directly than it might seem. Heat storage in ocean depths affects climate stability. Carbon sequestration in deep sediments influences atmospheric composition. Nutrient cycling supports surface productivity. These connections mean that understanding deep environments benefits more than scientific curiosity alone. From a biological standpoint, the deep ocean demonstrates flexibility in life's design. Chemosynthesis shows that sunlight is not the only viable energy source. Pressure adaptation shows that high mechanical stress does not prevent biological function. Darkness shows that sensory systems evolve to match available information rather than relying on one specific modality. These lessons extend beyond marine biology. They influence planetary science, biotechnology, environmental policy, and even philosophical reflection about life's resilience. Studying deep ecosystems often prompts reconsideration of what conditions are necessary for life and how adaptable living systems can be. Public perception continues evolving as exposure increases. Documentary footage, educational outreach, and scientific communication gradually replace older monster narratives with ecological understanding. The sense of alienness often shifts toward curiosity once context becomes clear. Still, a certain quiet fascination tends to remain. Watching bioluminescent organisms drift in darkness, observing slow-moving fish adapted to immense pressure, or seeing geological features hidden kilometers below the surface carries a sense of scale that is difficult to experience elsewhere. It is not about fear or exaggeration. It is about recognizing that much of our planet operates beyond everyday human experience. Scientific humility often grows from that recognition. The realization that large portions of Earth remain incompletely explored encourages caution in assumptions. It also motivates continued investigation. Educational value follows naturally. Learning about deep-sea ecosystems encourages interest in physics, chemistry, biology, engineering, and environmental science. Interdisciplinary research thrives in oceanography because multiple factors interact simultaneously. There is also a practical conservation dimension. Protecting habitats requires understanding them first. As exploration reveals biodiversity and ecological complexity, arguments for careful management strengthen. Cultural storytelling adapts gradually. Modern narratives increasingly emphasize discovery and stewardship rather than danger. This shift reflects improved knowledge and changing societal priorities. Technological advancement will likely continue accelerating exploration. Autonomous vehicles, improved sensors, long-duration observatories, and advanced imaging techniques promise clearer insights in coming decades. Future discoveries may challenge current assumptions just as hydrothermal vents once did. Science remains open to revision when evidence accumulates. Throughout all of this, the deep ocean remains quiet in a literal sense compared with surface environments. Sound travels efficiently there, but large-scale disturbances are less frequent. Visual activity appears subdued because energy conservation dominates. That quietness can be calming when viewed without preconceived fear, and perhaps that is the most balanced takeaway. The deepest parts of the ocean are not alien in origin, but they are different enough to remind us how adaptable life can be. They encourage curiosity without urgency, observation without alarm, and a steady awareness that exploration is an ongoing process rather than something completed. If you've stayed with this slow exploration from surface light down to total darkness, you now have a clearer picture of why those environments look the way they do. Not because they belong somewhere else, but because they belong exactly where they evolved, in a part of Earth that most people will never visit directly, yet which quietly supports the broader systems we all depend on.